Picture the magnets you know, the ones stuck to your fridge or holding up a child's drawing. They all have two ends, a north and a south. You can't have one without the other. But what if you could? What if you could hold a particle in your hand that was a pure North Pole, a solitary, independent magnetic charge, all on its own? This isn't just a quirky thought experiment. It's a prediction at the very frontier of physics, pointing to a particle so elusive it has never been conclusively found, yet its existence could rewrite our understanding of the cosmos. This is the story of the magnetic monopole. For decades, it has been a ghost in the machine of theoretical physics, a missing piece of a puzzle so grand that finding it would confirm some of our most ambitious ideas about how the universe works. Grand Unified Theories, or GUTS, which aim to weave the fundamental forces of nature into a single, elegant tapestry, practically demand that monopoles exist. They are not just a possibility, but a necessary consequence of a universe that began in a state of perfect symmetry. This journey into the heart of theoretical physics is about more than just confirming a prediction. It's about touching the very blueprint of reality. The hunt for the magnetic monopole is a quest to understand the conditions of the first fleeting moments after the Big Bang, a time when the forces we see as separate today, electromagnetism and the nuclear forces, were one and the same. The existence of monopoles is a direct relic from that era, a frozen fingerprint of a hotter, denser, and more unified cosmos. Imagine that, finding a particle today that is a direct messenger from the birth of everything. It carries with it the secrets of why our universe is the way it is, why matter exists, and what truly holds the fabric of space and time together. This search connects the impossibly large scale of the cosmos with the unimaginably small world of quantum particles, bridging gaps in our knowledge that have persisted for a century. So, as we embark on this exploration, we're not just cataloging facts, we're stepping into a detective story written across the entirety of existence. We will delve into why these particles are so crucial to our theories, how scientists across the world are trying to find them with incredibly sensitive experiments, and what their discovery would mean for the future of technology and our fundamental place in the universe. This is a story of human curiosity reaching for the stars, armed with mathematics and monumental machines, seeking to answer one of physics' most profound questions. Get ready to see the magnets on your refrigerator in a completely new light, because we are about to explore one of the most exciting and consequential chases in modern science. To truly grasp why this idea is so revolutionary, you first need to understand the foundation it would change. Our modern world, from the power grid to the smartphone in your pocket, runs on our understanding of electromagnetism, a set of rules elegantly captured by James Clerk Maxwell's equations in the 1860s. These four beautiful formulas describe everything about how electric and magnetic fields work, how they create light, and how they propagate as waves. But there's a subtle asymmetry in this foundational bedrock. In the world of electricity, you can have isolated charges. You can have a single, solitary positive proton or a single negative electron, and they exist just fine on their own. Yet, in the world of magnetism, as we've always known it, this is impossible. You can break a magnet in half, expecting to isolate a north pole, but you don't get a lone north. You instantly get a new, smaller magnet with its own north and south pole. This fundamental difference has been a quiet, accepted quirk of physics for over a century and a half. A magnetic monopole would erase that quirk. The name itself gives it away: mono for single, pole for magnetic pole. It is hypothesized to be an elementary particle that is a pure source of a magnetic field. One particle would be a pure north pole, another a pure south pole, existing independently in the universe. Finding one would be the magnetic equivalent of finding an electron, a particle with a single, defined electric charge. The implications of this for Maxwell's equations are profound. The equations are already stunningly powerful, but they contain a mathematical zero where the term for a magnetic charge would go, reflecting the fact that we've never observed one. The confirmed discovery of a monopole would fill in that zero with a new, fundamental constant of nature, a magnetic charge. This would not break the equations, it would complete them, introducing a perfect, beautiful symmetry between the descriptions of electricity and magnetism. They would become true partners, two sides of the same coin, described by mathematics that treats them with equal footing. Think of it like a previously unknown family member showing up and making a family tree suddenly make perfect sense. Everything clicks into place. This symmetry is more than just a mathematical nicety. It suggests that at the deepest level, the universe operates on principles of harmony and balance that we are only just beginning to perceive. It would validate a hunch that physicists have held for a long time, that the apparent asymmetries we see in the low-energy world around us are often just a frozen, broken version of a much more symmetric reality that existed at the birth of the cosmos. The search for the monopole, therefore, is not a hunt for a mere curiosity. It is a direct test of whether this profound and beautiful symmetry is woven into the very fabric of our reality. But this beautiful symmetry leads us to a deeper question. If magnetic monopoles are so elegant and necessary for a complete picture, why have we never seen one? The answer lies not in our current, relatively calm universe, but in its violent, searingly hot birth. To understand that, we need to step into the realm of grand unified theories, or GUTS, which represent one of the most ambitious quests in all of physics. For most of the last century, we've described the universe using two foundational pillars: the standard model of particle physics, which explains three of the four fundamental forces: the electromagnetic force, the weak nuclear force responsible for radioactive decay, and the strong nuclear force that holds atomic nuclei together, and Einstein's general relativity, which describes the force gravity. These frameworks are spectacularly successful, but they are separate. They speak different mathematical languages and they don't quite fit together, especially under the extreme conditions of the early universe. Grand unified theories are the attempt to bridge that first gap, to weave the electromagnetic, weak, and strong forces into a single, unified force described by one magnificent equation. The core idea of GUTS is symmetry. Picture the universe just a fraction of a second after the Big Bang, an environment of almost unimaginable energy and temperature. In that inferno, the distinctions we see today didn't exist. The electromagnetic force and the weak and strong nuclear forces were not separate entities. They were all manifestations of a single, primordial superforce. The particles we know today, electrons, quarks, and so on, were also indistinguishable. As this super-hot, dense universe expanded and cooled in its first moments, something monumental happened. It underwent a series of phase transitions, much like steam condensing into water or water freezing into ice. With each transition, a piece of the original perfect symmetry was lost or broken, and a new, distinct force froze out into existence. First, the strong force separated, and later, the electromagnetic and weak forces split. What was once one became many, and the unified laws fractured into the separate rules we study today. This is where magnetic monopoles enter the stage, not as optional extras but as unavoidable relics. Think of these phase transitions in a more tangible way. Imagine a vast, perfectly flat sheet of something that represents the unified field, a state of perfect symmetry. Now, as the universe cools, this field has to choose a new state, a new value that breaks the symmetry. It's like a vast dinner table covered with a perfectly smooth tablecloth. As it cools, it must form wrinkles, but because the table is so vast, different regions can't communicate with each other fast enough to coordinate which way to wrinkle. One region might choose to wrinkle upward, while the region right next to it wrinkles downward. Where these different regions of choice, these different domains of broken symmetry meet, a defect forms. In the case of the cosmic phase transition predicted by grand unified theories, these defects are not mere wrinkles in a tablecloth. They are incredibly dense, stable knots in the fabric of spacetime itself. These knots are what we call magnetic monopoles. Scientists refer to them as topological defects or solitons. Topological refers to properties that remain unchanged even when you stretch or bend an object, like the number of holes in a donut. A monopole is a topological defect because it is a stable, particle-like knot that cannot be smoothed away. It is a permanent feature of the cosmic landscape, a remnant of a more ordered past. The mathematics shows that when a grand unified symmetry breaks in the specific way these theories describe, the formation of these magnetic knots isn't just likely, it's mandatory. The early universe would have been flooded with them, a cosmic residue of its explosive birth. Their predicted properties are as staggering as their origin. A grand unified monopole wouldn't be some tiny, faint thing. It would be astronomically heavy, potentially as massive as a bacterium, which for a subatomic particle is almost incomprehensibly huge, and it would possess a magnetic charge that is quantized, a multiple of a fundamental unit, perfectly completing the symmetry Maxwell first wrote down. The hunt, therefore, is for a fossil, a cosmic dinosaur bone that holds the key to understanding the universe's first moments. The idea of a solitary magnetic pole might seem like a modern ambition, but its theoretical roots run surprisingly deep, reaching back to the mind of one of the 20th century's greatest physicists, Paul Dirac. In 1931, while the world was grappling with the profound implications of the new science of quantum mechanics, Dirac published a paper that was both subtle and explosive. He wasn't trying to unify the forces of the cosmos. He was focused on a different kind of puzzle, one of mathematical beauty and consistency. He realized that the then new framework of quantum mechanics, with its wave functions and probabilities, didn't just allow for the existence of a magnetic monopole, it practically invited it in, so long as you accepted one other fundamental truth about the universe, that electric charge is quantized. We take this for granted today, but it was a key insight. Electric charge doesn't come in a continuous spectrum. It only appears in discrete, indivisible multiples of a fundamental unit, the charge of the electron. You can have 1 electron's worth of charge or 2, but never 1.5. Dirac's genius was to show that if just one magnetic monopole, a single isolated north pole, existed anywhere in the universe, it would immediately provide a stunningly simple explanation for why electric charge is quantized in this way. He derived a now famous formula, the Dirac quantization condition. This condition creates a direct mathematical bridge between the world of electricity and the world of magnetism. It states that the product of the elementary electric charge and the elementary magnetic charge must be a multiple of a specific number involving Planck's constant, the fundamental unit of quantum action. In essence, the existence of a monopole with a specific magnetic charge would force electric charge to come in those discrete packets we observe. It's a two-way street. If charge is quantized, monopoles are possible, and if a monopole exists, charge must be quantized. This was a breathtaking connection. Dirac had found that two seemingly unrelated facts, the discrete nature of electric charge and the potential for isolated magnetic poles, were deeply intertwined, two consequences of a single, deeper quantum reality. To make this abstract idea a bit more tangible, picture the universe as a vast, invisible landscape governed by quantum rules. An electric charge moving through this landscape is described by a quantum wave. Now, imagine placing a magnetic monopole somewhere in this universe. Dirac showed that for the wave describing an electron to remain consistent, for its phase to be single-valued as it travels around the monopole, the magnetic charge of that monopole and the electric charge of the electron must satisfy his precise formula. It's like a cosmic lock and key. The monopole is the lock, and the quantization of electric charge is the key that fits it perfectly. Without the lock, you might not understand why the key has its particular shape. This was a monumental argument. It wasn't based on grand unification or the early universe. It was based purely on the internal consistency of quantum mechanics itself. Dirac had shown that the universe would be more logical, more complete, if monopoles were part of it. His work transformed the monopole from a mere mathematical curiosity into a legitimate object of scientific pursuit. It gave physicists a concrete, testable prediction about the strength of the magnetic charge a monopole should carry. The Dirac monopole, as it came to be known, would have a magnetic charge that is 68.5 times stronger than the fundamental unit of electric charge, a significant and detectable value. For decades, this Dirac prediction was the primary motivation for experimenters. They began looking everywhere, in cosmic rays raining down from space, in ancient rocks that might have trapped such a particle, and later in particle accelerators where they hoped to create one. While those early searches came up empty, Dirac had laid the essential groundwork. He provided the first compelling, mathematically rigorous reason to believe that our universe could, and perhaps should, host these solitary magnetic particles, setting the stage for the even more dramatic predictions that would come decades later from grand unified theories. Dirac's mathematical elegance set the stage, but grand unified theories took the concept of the magnetic monopole and catapulted it into an entirely new realm, not just of possibility, but of cosmic inevitability. These theories, however, came with a staggering prediction that immediately explained why we aren't tripping over monopoles in our everyday world. The monopoles spawned from the grand unification phase transition aren't just heavier than ordinary particles. Their predicted mass is almost beyond human comprehension. We're talking about a scale of 10 to the 16 giga-electronvolts. To put that number in perspective, a proton, the workhorse at the heart of every atom, has a mass of about 1 giga-electronvolt. The most powerful particle accelerator ever built, the Large Hadron Collider, can smash protons together at energies around 13,000 giga-electronvolts. That's an incredible achievement, but it's a mere 10 trillion times less energy than what would be needed to create a single grand unified monopole. The sheer magnitude of this number establishes a fundamental chasm between our current technological capabilities and the energy scales at which the universe truly unified. This incredible mass isn't an arbitrary figure, it's a direct consequence of the physics of symmetry breaking. The mass of a monopole is intrinsically tied to the energy scale at which the unification of forces occurred. Think of it like the energy required to create a defect in a material. If you want to create a crack in a flimsy piece of plastic, it doesn't take much force. But if you want to create a similar defect in a super tough alloy of titanium, you need a monumental amount of energy. The early universe at the moment of grand unification was like that titanium, an environment of unimaginable density and power. The monopole is a knot, a topological kink in the very fields that define reality, and untying that knot or creating a new one requires recreating those primordial conditions. The 10 to the 16 giga-electronvolt mass is essentially the fossilized energy of that epoch, a direct measure of the tremendous power that was coursing through the cosmos when it was just a fraction of a second old. This colossal mass has profound implications for how we search for these particles and why they are so elusive. Since we cannot possibly hope to produce them in any man-made collider for the foreseeable future, our only chance of finding one is to look for relics, the ones that were forged in the Big Bang itself and have been drifting through the cosmos ever since. But here we encounter another puzzle, one so severe that it nearly derailed the entire concept of grand unification. If the theories are correct, and the early universe was a chaotic soup of domains forming as the cosmos cooled, the calculations suggested it should have produced a veritable plague of monopoles. The universe should be absolutely flooded with them, with a density so high that their collective mass would have caused the cosmos to collapse back on itself long before galaxies, stars, or planets ever had a chance to form. The fact that our universe is old, vast, and mostly empty is direct observational evidence that this monopole overdose never happened. This was the infamous monopole problem, a glaring contradiction between elegant theory and observable reality. This crisis in cosmology was ironically the very catalyst for one of the most transformative ideas in modern physics, cosmic inflation. To resolve the monopole problem, physicists proposed that the infant universe underwent a period of hyper-accelerated, exponential expansion. For a fleeting moment, the fabric of space-time itself stretched at a rate faster than the speed of light. This inflationary epoch would have had a dramatic effect on the nascent monopole population. It would have diluted them, spreading the relatively few monopoles that formed in our local patch of the universe so incredibly thin across an unimaginably vast volume that their density became negligible. The once overcrowded monopole soup was transformed into an incredibly sparse cosmic broth, with perhaps only one of these massive particles residing in a volume of space as large as our entire solar system. This elegant solution not only saved grand unified theories from an observational death sentence, but also explained other profound features of our universe, like its overall flatness and uniformity. So the very scarcity of monopoles that makes them so hard to find is itself a powerful piece of evidence for one of our most successful cosmological models. Their absence tells a story as important as their presence ever could. To grasp how something as exotic as a magnetic monopole could be forged in the fires of the Big Bang, it helps to think about a more familiar process: water freezing into ice. When a pond freezes on a cold night, the ice doesn't form a single, perfectly ordered crystal all at once. Instead, tiny crystals of ice begin to form independently at different spots across the surface. Each of these small crystals has its own internal orientation, its own preferred alignment for its molecular lattice. As these growing patches of ice meet and merge, they create boundaries. Where one crystal oriented in one direction meets a crystal oriented in another, a line of imperfection forms, a flaw in the otherwise regular structure. This is a topological defect in the ice, a place where the orderly arrangement of molecules is forced to kink and contort to accommodate the clash between different domains. The early universe underwent a remarkably similar process, but on a cosmic scale and involving the fundamental fields that define reality itself. In the language of physics, these imperfections are known as topological defects, and they are stable, persistent structures that can form when a system undergoes a phase transition and its symmetry is broken. The topological part of the name is key. Topology is the branch of mathematics concerned with properties that remain unchanged even when an object is stretched, bent, or twisted, so long as it isn't torn or glued. A classic example is a coffee mug and a donut. To a topologist, they are the same because each has exactly one hole. You can theoretically morph a donut into a mug without breaking it. A topological defect, then, is a stable configuration in a field that cannot be smoothly transformed away. It's a knot or a kink that is topologically protected, much like the hole in the donut can't be removed by simply smoothing out the dough. In cosmology, these defects aren't just interesting curiosities. They are fossilized relics of the universe's phase transitions, and they come in different dimensions. There can be one-dimensional defects called cosmic strings, which are incredibly dense, thread-like cracks in spacetime. There can be two-dimensional defects known as domain walls, vast, sheet-like structures that would contain staggering amounts of energy. And then there are the zero-dimensional, point-like defects. These are our magnetic monopoles. So how does a grand unified theory lead directly to the creation of these point-like knots? Recall that in the first instance after the Big Bang, the electromagnetic, weak, and strong nuclear forces were unified into a single, symmetric force. The state of the universe was described by a grand unified field that was in a state of perfect symmetry, much like the liquid water in our pond, where every point and every direction is equivalent. As the universe expanded and cooled, it crossed a critical temperature threshold. At this point, the symmetric state became unstable, and the universe had to choose a new, stable state, a process called spontaneous symmetry breaking. This is the moment the water of the unified field began to freeze. But just like in the freezing pond, there was no master controller telling every part of the universe which new state to pick. Regions of space that were too far apart to communicate with each other, separated by more than the distance light could have traveled in that tiny time, made their choices independently. Imagine a vast, infinite field where at every point an arrow can point in any direction in an abstract, high-dimensional space. In the hot, symmetric phase, all these arrows are wildly fluctuating with no preferred direction. As the universe cools, the arrows must settle down and point in a specific direction to achieve the new, stable, broken symmetry state. But in one region of space, the arrows might spontaneously choose to all point north, while in a neighboring region, they might all choose to point south. Where these two domains meet, you have a problem. The arrows in the north domain can't smoothly connect to the arrows in the south domain. There has to be a point, a location, where the arrow is forced to point in every direction at once to bridge the gap. It's like trying to comb a hairy ball flat. The famous hairy ball theorem in mathematics tells us you will always end up with at least one crown, a point where all the hairs meet. In the cosmic field, that point, that unavoidable crown, is a magnetic monopole. It is a topological knot where the field cannot be smoothly defined, and this knot manifests itself as a solitary, point-like source of magnetic charge. These monopoles are not merely artifacts of a mathematical model. They are predicted to be incredibly robust and stable objects. Because their existence is tied to the topology of the field, they cannot simply decay or dissipate. You can't untie the knot without restoring the original high-energy symmetric state, an event that would require energies far beyond anything in our current universe. This gives them a cosmic permanence, making them perfect candidates for relics that could have survived nearly 14 billion years of cosmic evolution. They are not made of matter in the conventional sense. They are knots of condensed energy, crystallized fragments of a more symmetric age, drifting through the galaxy as permanent testament to the universe's tumultuous birth. Finding one would be like holding a piece of that first cosmic ice, a direct sample of the moment the forces of nature as we know them were born. If the sheer mass of a grand unified monopole makes it impossible for us to create one, and cosmic inflation has rendered them incredibly rare, you might wonder how we could ever hope to detect such an elusive relic drifting through space. The answer lies in one of their most bizarre and dramatic predicted properties, their ability to make protons decay. This is not a minor side effect. It is a spectacular process that challenges our understanding of the very stability of matter. We are taught that a proton is essentially forever, a stable bedrock of the atomic nuclei that make up our bodies and our world. Indeed, experiments have shown that if a proton does decay on its own, its lifetime is staggeringly long, exceeding 10 to the 34 years, far longer than the current age of the universe. But bring a proton into contact with a grand unified monopole, and that near-infinite lifetime could be slashed to a tiny fraction of a second. This remarkable effect is known as the Rubikov-Kallen effect, named after the physicists who worked out its details, and it turns the monopole from a passive fossil into an active, destructive agent. The mechanism behind this catalysis is deeply rooted in the monopole's nature as a knot in the grand unified field. Remember, this particle is a direct conduit to the era when the strong nuclear force and the electroweak force were one. Its core, even today, is a region where the laws of grand unification are temporarily restored. Think of the monopole not as a simple magnet, but as a tiny, ultra-dense portal to a more symmetric state of the universe. When an ordinary proton, which is made of quarks bound together by the strong force, approaches this portal, the immense and unusual topology of the monopole's field disrupts the very identity of those quarks. In the grand unified picture, quarks and the particles responsible for radioactive decay, called leptons, are not fundamentally distinct. They are different facets of the same unified particle. The monopoles field acts as a catalyst, providing the perfect environment for a quark, one of the fundamental constituents of the proton, to change into an anti-lepton. Here is how the catastrophic sequence unfolds. A proton, which consists of 2 up quarks and 1 down quark, ventures near the monopole. The weird geometry of the monopole's magnetic field and its unified core allow a process that is otherwise forbidden. One of the quarks inside the proton is effectively annihilated, transforming not into another quark but directly into a positron, which is the antimatter counterpart of the electron. This transformation violates the conservation of baryon number, a quantum rule that normally prevents protons from decaying. With one of its core constituents suddenly gone, the proton instantly and violently falls apart. The remaining quarks reconfigure, releasing a burst of energy and producing a particle called a pion, which itself rapidly decays into gamma rays. The entire event, from stable proton to a shower of new particles, happens almost instantaneously because of the monopole's presence. It's as if the monopole holds a master key that unlocks a hidden door in the laws of physics, a door that allows matter to unravel back into pure energy. To grasp the sheer power of this catalysis, imagine a single, stationary monopole resting somewhere, perhaps deep within the Earth or drifting through space. It wouldn't need to move quickly to be detected. As it sits there, protons from the surrounding matter from the rock, water, or air would naturally bump into it due to their own random thermal motion. Each encounter could trigger a decay. A single monopole could, in theory, consume the atoms around it at a measurable rate, leaving behind a trail of telltale radiation. The signature of this process is very specific. It would produce a continuous, predictable signal of particle showers, unlike the random background noise from other natural radioactive processes. This gives experimenters a very clear, albeit exceedingly rare, signal to hunt for. This incredible prediction has spawned a whole class of ambitious experiments designed to catch a monopole in the act of destroying matter. Since these particles are so massive, they would be relatively slow-moving if they are relics from the Big Bang, traveling at speeds far less than the speed of light. This has led scientists to build enormous, ultra-sensitive detectors deep underground, shielded from cosmic rays, to listen for the distinctive pop of a catalyzed proton decay. These detectors are often massive tanks filled with ultra-pure water or other materials, surrounded by a forest of sensitive light sensors. If a monopole were to drift through such a tank, it would catalyze the decay of protons in the water molecules, producing flashes of light called Cherenkov radiation that the sensors would pick up. Other experiments search for evidence of monopoles that might have been trapped by the Earth's magnetic field and accumulated in ancient rocks or deep-sea sediments over billions of years, looking for microscopic scars or traces of elements that would be left behind by their destructive passage. The implications of discovering proton decay catalysis are twofold, each more profound than the last. Firstly, it would provide a direct and unmistakable confirmation of grand unified theories. Observing a single event of this kind would be like finding a signed confession. It wouldn't just suggest that GUTS are correct, it would demonstrate their physical reality in the most dramatic way possible by showing a particle that actively enforces the unified laws. Secondly, and perhaps more philosophically unsettling, it reveals that the stability of matter is not an absolute truth but a conditional one. The protons that constitute every atom in your body are stable only because monopoles are so incredibly rare in our present-day universe. In a region densely populated with these relics, matter as we know it could not exist. Atoms would disintegrate almost as soon as they formed. Our very existence, then, is contingent upon a specific and sparse arrangement of the cosmos, a universe that inflated enough to dilute not only monopoles, but also the threat they pose to the integrity of matter itself. This elegant theoretical framework, with its prediction of stable, massive monopoles created in the fiery dawn of time, immediately ran headlong into a formidable observational wall, creating what cosmologists call the monopole problem. Grand unified theories, in their simplest and most beautiful form, presented a clear and startling calculation. Given the incredibly high energy of the early universe and the mechanism of symmetry breaking, the process of domain formation should have been astoundingly efficient. The mathematics suggested that these topological knots would have been produced in staggering numbers, so plentiful that their density would have been comparable to photons in the cosmic microwave background. If that were true, the total mass carried by this sea of monopoles today would be so immense that the gravitational pull of all that matter would have caused the universe to collapse back on itself in a big crunch when it was only a few tens of thousands of years old. The very existence of our 14-billion-year-old cosmos, with its galaxies, stars, and planets, stands as direct, undeniable evidence that this catastrophic monopole overload never occurred. Our universe is ancient, vast, and for the most part empty, which means the density of these massive relics must be incredibly, almost vanishingly small. This glaring contradiction between the elegant predictions of particle physics and the hard facts of observational cosmology represented a profound crisis for grand unified theories in the late 1970s. The solution to this existential threat emerged in the form of one of the most revolutionary ideas in modern cosmology: cosmic inflation. Proposed initially by Alan Guth and then refined by others like Andre Linde and Paul Steinhardt, inflation posits that the universe underwent a brief, unimaginably violent period of hyper-accelerated expansion in the very first instant of its life, far before the grand unification phase transition was even complete. To grasp the sheer scale of this event, picture the entire observable universe, all hundreds of billions of galaxies, compressed into a volume smaller than a single proton. Then, in a span of time so short it defies human intuition, perhaps as brief as 10 to the negative 36 seconds, this subatomic speck of spacetime expanded by a factor of at least 10 to the 26. It's an expansion so rapid that it exceeded the speed of light, not for any object within space, but for the fabric of spacetime itself, a possibility allowed by general relativity. This wasn't a gentle, steady growth. It was a stupendous, exponential stretching of the cosmic fabric. This inflationary burst acted as the ultimate cosmic diluting agent for the monopole problem. Think of a single drop of intensely concentrated dye in a tiny thimble of water. That dye represents the initial, dense population of monopoles produced in the earliest pre-inflationary universe. Now, imagine instantly pouring that thimble into an ocean the size of our entire solar system and stirring it vigorously. The drop of dye would be spread so thin that finding a single molecule of it in any given liter of seawater would be nearly impossible. Cosmic inflation did precisely this to the monopoles. It took the patch of universe that would one day become everything we can observe and stretched it to such an enormous volume that the primordial monopoles within it were flung incredibly far apart from one another. Their density plummeted from a catastrophic overload to a negligible trace, perfectly consistent with the fact that we don't see them dominating the cosmos today. The inflation theory didn't prevent monopoles from forming. It simply separated them so effectively that encountering one became an event of extraordinary rarity. This resolution is beautifully elegant because it doesn't just solve one problem. It provides explanatory power for several other profound cosmological puzzles simultaneously. For instance, the cosmic microwave background, the remnant heat from the Big Bang, is incredibly uniform in all directions. Without inflation, there's no reason why regions of the universe on opposite sides of the sky, which could never have been in thermal contact, should have the exact same temperature. Inflation solves this by positing that the entire observable universe was once a tiny, causally connected region that was stretched to cosmic proportions, preserving its initial uniformity. Furthermore, inflation naturally explains why the geometry of the universe appears so remarkably flat. The incredible stretching during the inflationary epoch would have flattened the cosmic curvature, much like blowing up a balloon to an immense size makes its surface appear flat to a tiny ant crawling on it. The monopole problem, which seemed like a fatal flaw, became the key motivation for a theory that now stands as a cornerstone of modern cosmology. The very absence of monopoles, therefore, is one of the strongest indirect pieces of evidence we have that the universe did indeed experience this fantastic inflationary growth spurt in its first fleeting moments. Given the profound implications of their discovery, it's no surprise that physicists have been searching for magnetic monopoles for nearly a century, devising ever more ingenious and sensitive experiments to snare this cosmic ghost. The earliest searches were relatively simple, born from the theoretical elegance of Dirac's work. Scientists reasoned that if monopoles were out there, they might be arriving from space as part of the cosmic ray shower that constantly bombards our atmosphere. They used stacks of photographic emulsion similar to old camera film and sent balloon-borne detectors high into the stratosphere. The idea was that a heavily ionizing, massive monopole would leave a distinctive, thick track as it plowed through the emulsion, a signature unlike any known particle. Others looked for monopoles that might have been trapped in ancient, stable geological formations like mica or deep-sea manganese nodules. The logic was that over millions or even billions of years, a monopole could have become embedded in these materials, leaving a trail of atomic damage or altered isotopic ratios. While these pioneering efforts demonstrated immense scientific creativity, they all returned the same result: null. No conclusive, reproducible evidence for a monopole was ever found. The continued lack of a positive detection only fueled the need for more sophisticated and direct methods. This led to the development of a classic and beautifully simple technique known as the induction search. The principle is straight out of a freshman physics textbook. If a magnetic monopole is indeed a solitary magnetic charge, then moving it through a loop of wire should induce an electric current in that loop. This is the direct consequence of Maxwell's equations, now finally made whole. In a standard loop, moving a regular magnet with both a north and south pole through it produces no net current, the effects cancel out. But a single north pole passing through the loop would create a very specific, very sudden, and very large current spike, a clear, unambiguous signal. This principle has been the backbone of several major experiments, often using superconducting coils. In a superconductor, electrical resistance vanishes, allowing an induced current to persist and be measured with extraordinary sensitivity. Some of the most famous of these induction experiments were conducted by physicist Blas Cabrera in the 1980s, who built a delicate multi-loop superconducting detector and watched it for months, hoping for that one definitive spike. One day in February of 1982, his detector registered an event. The signal was perfect, a single, large current jump that precisely matched what was predicted for a magnetic monopole passing through his apparatus. For a thrilling moment, it seemed like the search was over. The event, now famously known as the Valentine's Day monopole, caused a sensation in the physics community. However, science requires replication. Despite years of further operation with even more sensitive detectors, that singular event never repeated. Without a second day to point to confirm it, the result remains an enigmatic, tantalizing, but ultimately unverified blip in the history of physics. It could have been a rare, unknown instrumental glitch, a piece of cosmic dust, or perhaps it was a genuine monopole that simply never came back. This episode highlights the immense challenge of the hunt. You must build a detector sensitive enough to see a needle in a cosmic haystack, but also robust enough to rule out every other possible source of that needle. Today, the search has evolved into a global, multi-pronged effort, leveraging the world's most powerful particle accelerators and deepest underground laboratories. A flagship modern experiment is the Monopole and Exotics Detector at the LHC, or MOEDL, located at CERN. MOEDL approach is both classic and innovative. Rather than relying on electronic signals alone, it uses stacks of plastic nuclear track detectors, a bit like high-tech flypaper for exotic particles. If a highly ionizing particle like a massive monopole passes through these plastic sheets, it leaves a trail of damaged polymer chains. By chemically etching these plastics, the tiny, submicroscopic trails are enlarged into pits that can be seen and analyzed under a microscope. The sheer size and density of the monopole would create a track that is unmistakable compared to those left by known particles like protons or muons. MOEDL is positioned around the LHC's interaction points, hoping to catch a monopole produced in the high-energy proton collisions, even if the energy is far below what's needed to create one from scratch. The theory is that the collision could act like a trigger, liberating a pre-existing monopole that might be bound to the material of the detector or even creating a pair through a rare quantum process. Alongside MOEDL, other experiments continue the search using different strategies. Large, underground detectors originally built to look for proton decay or neutrino interactions like Super Kamiok and in Japan also serve as monopole hunters. These massive tanks, filled with tens of thousands of tons of ultra-pure water and lined with sensitive light detectors, are watchful for the telltale Cherenkov radiation glow that would be produced if a magnetically charged monopole moved through the water. Even a slow-moving monopole would interact strongly with the water molecules, producing a continuous, steady glow of light unlike the sharp flashes from other particle interactions. Other researchers continue to scan materials from the Moon, brought back by the Apollo missions, or from the depths of the ocean, hoping to find one that has been trapped for eons. The persistence of these varied approaches underscores a fundamental truth. No one is entirely sure what the perfect detection method is, so scientists are wisely covering all bases, from the depths of the Earth to the energies of our largest machines. So, after all this effort, spanning generations and employing some of the most advanced technology ever created, why have all these searches come up empty? The null results are not a failure, they are data. They tell us something very important about our universe. The most straightforward explanation is the one provided by cosmic inflation. Monopoles are simply incredibly, almost impossibly, rare in our local patch of the cosmos. The density of these relics, thanks to that primordial stretching, is so low that the probability of one passing through a detector the size of Earth in a human lifetime is vanishingly small. We are looking for a particle that might only appear once per galaxy every 1,000 years. Another possibility is that our theoretical models, while beautiful, might be slightly off. Perhaps the grand unification scale is even higher than we think, making monopoles even heavier and rarer. Or maybe the specific way the symmetry broke in our universe was such that monopole formation was suppressed, a fluke of cosmic evolution that left our region of space relatively free of these topological knots. There's also a more practical challenge. We cannot be 100% certain of a monopole's exact properties. While we have strong predictions for its magnetic charge and mass, its interaction with matter could be subtler than our models assume, allowing it to pass through our detectors without leaving the dramatic signature we expect. Each null result helps us refine these models, narrowing the range of possible properties and guiding the next generation of experiments in this grand, ongoing cosmic quest. Because directly capturing a magnetic monopole remains an immense challenge, scientists have turned into cosmic detectives, looking for subtle clues and environmental footprints that such a particle might have left behind across the vastness of space. One of the most promising avenues involves scrutinizing the cosmic rays that continuously rain down upon Earth from all directions. These are not rays of light, but rather a shower of high-energy particles, mostly protons and atomic nuclei, traveling at nearly the speed of light. If magnetic monopoles exist as cosmic relics, they should be part of this natural particle radiation, albeit a fantastically rare component. Their detection would rely on their unique interaction with matter. A particle as massive as a grand unified monopole, even moving at a modest fraction of light speed, would carry an enormous amount of kinetic energy. As it plowed through a detector or even the atmosphere, it would not behave like a swift, lightly ionizing proton. Instead, it would be a slow, heavy cannonball, tearing through atoms and leaving an incredibly dense trail of ionization in its wake, a signal that would be unmistakably different from any other known particle. Experiments have been designed specifically to look for these super-heavy, super-slow particles in the cosmic flux. Some of the most sensitive searches have been conducted using large arrays of plastic track detectors, similar to those used in the Mo-Edel experiment, but deployed in high-altitude balloons or on spacecraft to get above the shielding of the atmosphere. Others have used ancient mica, a mineral that acts as a perfect, natural recording medium over geological timescales. If a monopole had passed through a piece of mica 100 million years ago, its intense ionization trail would have left a permanent, submicroscopic wound in the crystal structure. By carefully etching the mica with acid, these trails can be enlarged and studied under a microscope. The length, width, and structure of such a trail could, in theory, reveal the passage of a monopole. While these searches have placed ever more stringent upper limits on the flux of monopoles, telling us that they cannot be more common than a certain vanishingly small number, a definitive, universally accepted track has yet to be found, pushing the possible monopole population further into the realm of the exceedingly scarce. Beyond looking for the particles themselves, astrophysicists search for the indirect, large-scale imprints monopoles would leave on the cosmos. A key area of investigation is the magnetic fields that permeate entire galaxies, including our own Milky Way. The origin of these vast, coherent magnetic fields is still a subject of active research. One compelling hypothesis is that they are seeded by a primordial population of magnetic monopoles in the early universe. Imagine the cosmos shortly after inflation, still incredibly dense and hot, with a sparse but significant number of monopoles and their opposite charge counterparts, anti-monopoles, drifting through the plasma. These particles, each a source of magnetic field, would have their own chaotic, random magnetic fields. As the universe evolved and structures like galaxies began to form, the gravitational collapse could have amplified and ordered these primordial magnetic fluctuations, stretching them into the large-scale, organized fields we observe today. Finding a concrete link between galactic magnetic fields and monopoles is extraordinarily difficult, as other mechanisms can also produce such fields, but it remains a tantalizing possibility that the magnetism we see writ large across the galaxy is the faded echo of a monopole-filled dawn. Perhaps the most dramatic and extreme environments where monopoles could reveal themselves are neutron stars. These are the ultra-dense, collapsed cores of massive stars, where matter is compressed to such a degree that a teaspoonful would weigh billions of tons on Earth. Their immense gravitational fields act as powerful traps. If a monopole were to wander near a neutron star, it would be irresistibly pulled in and captured, just like a speck of dust falling to the ground. Once inside, the monopole would begin a fascinating and destructive journey. Drawn by the intense gravity, it would sink towards the star's core. Along the way, it would catalyze the decay of protons in the neutron-rich material, as described by the Rubikov-Kalin effect. This process would release a tremendous amount of energy in the form of heat. A single monopole could, in theory, provide a powerful and long-lasting heating source for an otherwise cold, dead neutron star. This leads to a remarkable observational test. Astronomers have observed a class of very old, isolated neutron stars known as millisecond pulsars. These stars are predicted to have cooled down to temperatures of just a few 100,000 degrees after hundreds of millions of years. However, some of them are observed to be significantly warmer than these cooling models predict. One potential explanation for this excess heat is the presence of a small number of magnetic monopoles within their cores, continuously generating energy by consuming the star's very matter. The monopole would act as a microscopic furnace, keeping the stellar corpse warm long after its nuclear fires have died out. While other explanations like residual friction or acoustic heating are also possible, the monopole hypothesis provides a clean, testable mechanism. If future observations could correlate unexpected heating in ancient neutron stars with other potential monopole signatures, it would build a powerful, albeit indirect, case for their existence. The search has also extended to the most cataclysmic events in the universe, gamma-ray bursts and supernova. Theoretically, if a monopole and an anti-monopole were to meet, they would annihilate each other in a flash of energy, much like an electron and a positron do, but on a vastly greater scale due to the monopole's enormous mass. This annihilation would release a tremendous burst of high-energy gamma rays. Some researchers have speculated whether certain types of short, unexplained gamma-ray flashes could be the signature of such monopole annihilation events. Similarly, the intense energy released in a supernova explosion could, in principle, create a shockwave that might accelerate any pre-existing monopoles in the vicinity to high speeds. If a monopole were then to strike a nearby celestial body like a planet or another star, the resulting energy release could leave a distinct mark. To date, no such event has been conclusively linked to monopoles, but the fact that scientists are mining data from the most violent processes in the universe for these subtle clues shows just how far-reaching the implications of their discovery would be. Each anomalous observation that cannot be explained by conventional physics becomes a small flicker of hope, a potential signpost pointing toward a hidden population of these mythical particles, forever altering our quest from a direct hunt to a patient, multifaceted interpretation of the cosmos's deepest secrets. While we have been scouring the cosmos and building colossal detectors without a definitive discovery, one of the most fascinating developments in this quest has occurred not in deep space, but in the quiet confines of materials science laboratories. Here, in a class of exotic substances known as spin ices, physicists have found something remarkable, not the fundamental cosmic monopole itself, but a stunningly accurate analog of one. These are what we call emergent phenomena, where the collective behavior of countless tiny components in a material gives rise to properties and particles that are not present in the individual parts. It's like watching a bustling city from high above. You can see traffic patterns and crowd movements that have a life of their own, even though they are just the result of many individual people making individual decisions. In spin ices, the collective dance of magnetic atoms conspires to create quasi-particles excitations that behave for all intents and purposes like magnetic monopoles, providing us with a powerful and tangible playground to test the concepts we've so far only theorized about. To understand how this is possible, picture the atomic structure of a spin ice material such as dysprosium titanate. Inside its crystal lattice, atoms of a magnetic element like dysprosium are arranged in a pattern of tetrahedrons, which are pyramid-like structures with 4 triangular faces. Each magnetic atom or spin acts like a tiny nanoscopic bar magnet. At extremely low temperatures, the rules of physics governing these spins lead to a unique and frustrated state. The system wants to minimize its energy, but the geometry of the tetrahedron makes it impossible for all the magnetic arrows to satisfy the ice rule, a condition where 2 spins must point inward and 2 must point outward at each corner, mimicking the proton arrangement in water ice. The result is a disordered yet rule-bound magnetic landscape. Now, if you add a little energy to this system, say, by applying a magnetic field or raising the temperature slightly, you can excite it. One specific excitation is like flipping a single magnetic arrow, but this simple local act has a dramatic, non-local consequence. It effectively creates a pair of defects in the magnetic structure. At one corner of the tetrahedron, you suddenly have 3 spins pointing in and 1 out. At the adjacent corner, you get 3 pointing out and 1 in. These 2 defects are the emergent monopoles. The point where 3 spins point inward and 1 outward behaves exactly like a source of magnetic field, a north magnetic charge. The point where 3 point outward and 1 inward acts like a sink, a south magnetic charge. They are born as a pair connected by a taut, invisible string of energetic tension called a Dirac string. But here's the truly magical part. In the spin ice, this string can break. The north and south quasi-particles can be pulled apart by an applied magnetic field, and they will then drift independently through the crystal lattice, interacting with each other through a magnetic force that follows the same inverse square law that real, fundamental monopoles would obey. You can literally watch them separate, move, and even recombine, all within the confines of a small crystal cooled to a fraction of a degree above absolute zero. They are not the massive, universe-altering particles predicted by grand unified theories. They are emergent quasi-particles, but their behavior is governed by the same mathematical principles. This makes them an incredible quantum simulator, a tabletop universe where we can experiment with the physics of magnetic charges in a controlled environment. The implications of this discovery are profound for both fundamental and applied science. For the first time, physicists can directly measure properties that were purely theoretical. They can probe how these monopole-like quasi-particles move, how they respond to magnetic fields, and even study their thermodynamics, how they contribute to the heat capacity and entropy of the material. Experiments have shown that these emergent monopoles can carry a quantized magnetic charge and that their density in the material can be controlled, much like tuning the concentration of electrons in a semiconductor. This has opened up the tantalizing possibility of magnetricity, the magnetic equivalent of electricity. Just as we can have electrical circuits where the flow of electrons constitutes an electric current, we could potentially create magnetic circuits where the flow of these magnetic monopole quasi-particles constitutes a magnetic current. This isn't science fiction. Researchers have already demonstrated the basics of this phenomenon in spin ice, observing magnetic currents and even measuring a magnetic Hall effect, where the flow of these charges is bent by an applied magnetic field. What spin ices teach us is that the concept of a magnetic monopole is robust and physically real, even if it emerges from a complex collective state. It validates the mathematical beauty of Dirac's and grand unified theory's predictions in a tangible, laboratory setting. While the search for the cosmic, fundamental monopole continues, these condensed matter analogues provide a crucial bridge between abstract theory and experimental reality. They show us that the laws of physics allow for the existence and dynamics of magnetic charges, giving us even more confidence that the solitary North Pole we seek in the cosmos might indeed be out there, waiting to be found. This parallel exploration enriches the entire quest, proving that sometimes, to find the secrets of the universe, we must also look closely at the extraordinary world hidden within the materials right here on Earth. This brings us to one of the most exhilarating questions in this entire quest. If we were to actually find and harness a magnetic monopole, what could we do with it? The answer stretches the imagination, pointing toward technological revolutions that could redefine the limits of computing, energy, and our entire relationship with the magnetic world. The key lies in the monopole's most fundamental property, its isolated magnetic charge. Think of our entire electronic civilization as being built on the flow of electric charge, the movement of electrons. But magnetism, as we currently use it, is a clumsy affair. We create magnetic fields by making electric currents run in loops, which is an inherently inefficient process. We manipulate the north and south poles of tiny magnets in tandem, never separately. A monopole would shatter this paradigm, opening the door to an entirely new form of technology, magnetricity, or the controlled flow of magnetic charge, operating with a directness and efficiency we can barely dream of today. The most immediate and profound impact could be in the realm of data storage. Our current hard drives and magnetic memory work by flipping the magnetic orientation of tiny domains on a spinning platter. Each domain is a miniature magnet with both a north and south pole, and we write a 1 or a 0 by forcing its orientation one way or the other. This is a bulk process. You're moving the entire magnetic entity. Now, imagine a storage medium built from an array of individual magnetic monopoles. A single, stable north pole sitting in a specific location could represent a 1, while its absence or the presence of a south pole could represent a 0. The act of writing data would no longer involve flipping a bulky magnet. It would involve precisely injecting or removing a single, point-like magnetic charge. This is the difference between rearranging entire books on a shelf to change a single word versus simply plucking out one letter and replacing it. The potential for data density is staggering. We could be talking about storage devices the size of a sugar cube capable of holding every byte of information humanity has ever created, with read and write speeds orders of magnitude faster than today's solid-state drives, because the fundamental act of data manipulation would occur at the most elementary level possible. Beyond sheer density, the stability of a grand unified monopole would be a game-changer. These particles, as topological defects, are predicted to be incredibly robust and immune to external perturbations that would easily corrupt conventional magnetic storage. Heat, stray magnetic fields, or even minor physical damage that would scramble the data on a traditional hard drive would likely leave a monopole-based memory cell completely unfazed. This inherent stability could lead to archival storage systems with virtually infinite lifetimes, preserving humanity's knowledge for millennia without degradation. Furthermore, the ability to have a persistent, quantized magnetic charge opens up radical new architectures for logic itself. We could design circuits where magnetic currents, rather than electric currents, perform computations. Since magnetic fields pass through most materials without interacting, these magnetic processors could be stacked in 3 dimensions without the crosstalk and heat dissipation problems that plague modern, densely packed silicon chips, leading to a new era of ultra-efficient, powerful computing. Perhaps the most transformative application, however, lies in the heart of the next computing frontier: quantum information. The field of quantum computing is a race to build a machine that harnesses the bizarre laws of quantum mechanics to solve problems that are intractable for even the largest supercomputers. But quantum states are notoriously fragile, easily collapsing from a useful superposition into a definite state through a process called decoherence. This is the single greatest obstacle to building a practical, large-scale quantum computer. Magnetic monopoles, with their unique topological origin, could offer a stunningly elegant solution. A topological qubit, the fundamental unit of a quantum computer, is one where information is encoded not in a fragile particle like an electron or a photon, but in the global topological properties of a system. Because these properties are immune to local disturbances, they are inherently protected from decoherence. It's like storing a message in the number of holes in a donut. You can stretch, bend, or twist the donut, but as long as you don't tear it, the message, the number of holes, remains intact. A magnetic monopole is the ultimate topological object. Its very existence is a knot in the fields of spacetime. This makes it a perfect candidate for hosting a topologically protected quantum state. Scientists speculate that a pair of monopoles, or a monopole interacting with another topological defect like a cosmic string, could form the basis of a qubit whose coherence time would be astronomically long compared to anything we can create in the lab today. Manipulating such a qubit would involve using their magnetic charges or moving them along precise paths, operations that would be far less error-prone than the laser pulses and microwave fields used to control today's delicate qubits. Building a quantum computer with even a handful of these topological qubits could allow us to perform calculations for drug discovery, materials science, and climate modeling that are currently beyond our reach, unlocking a new chapter of scientific and technological progress. The energy implications are equally profound. Consider the process of proton decay catalysis. While a threat to the stability of matter, it also represents an unimaginably dense source of energy. A single monopole could, in theory, be used as the core of a microscopic reactor, catalyzing the conversion of common hydrogen into pure energy with near total efficiency. The energy density would dwarf that of nuclear fission or fusion, as you would be tapping directly into the mass energy of protons themselves, the most abundant form of ordinary matter in the universe. Of course, the control and containment of such a power source would be a monumental challenge, but the sheer potential is a testament to the paradigm-shifting nature of this particle. On a more immediate scale, the ability to generate and control pure magnetic currents could revolutionize power transmission. Our electrical grid loses a significant amount of energy as heat due to electrical resistance in the wires. Magnetic fields, however, can travel through certain materials with minimal loss. A future magnetricity grid could transmit power across continents with almost perfect efficiency, fundamentally changing our relationship with energy generation and distribution. It's crucial to ground this speculation in reality. We are talking about a particle we have not yet found, one that is likely incredibly rare and massive. Harnessing it would require technologies we can scarcely conceive of, perhaps involving forces and field strengths far beyond our current engineering capabilities. Yet, this kind of visionary thinking is what has always driven science forward. The pursuit of the magnetic monopole is not just an academic exercise, it is a bet on the future of knowledge itself. It is the belief that by uncovering the most fundamental symmetries of the universe, we will inevitably unlock new principles that can be translated into world-changing technologies. From the solid-state physics of transistors to the quantum mechanics behind lasers, history has shown us time and again that understanding the deepest workings of nature provides the tools to build a better tomorrow. The magnetic monopole, this ghost from the dawn of time, may one day become the cornerstone of a technological civilization we are only just beginning to imagine. This journey into the heart of theoretical physics reveals that the magnetic monopole is far more than just a missing particle. It is a key that could unlock a deeper layer of reality governed by profound symmetries. At its core, the search for the monopole is a quest to understand why the universe is structured the way it is, and the principles that dictate its behavior. One of the most sacred and deeply tested principles in all of physics is known as CPT symmetry. This isn't just one idea, but a triple combination of three fundamental symmetries: charge conjugation, which swaps every particle with its antimatter counterpart; parity, which mirrors space, flipping left and right; and time reversal, which runs the clock backward. For decades, every test we've thrown at this combined CPT symmetry has shown it to hold perfectly. It is a cornerstone of our understanding, implying that the laws of physics are the same if you simultaneously flip all particles to antiparticles, view the universe in a mirror, and reverse the flow of time. The existence of magnetic monopoles is intricately woven into this tapestry. Their predicted properties, such as their quantized charge, are fully consistent with CPT invariance, and finding one would powerfully reinforce this foundational pillar. It would demonstrate that even an object as exotic as a solitary magnetic charge still plays by these ultimate cosmic rules, upholding the symmetry that underpins our most fundamental theories. Perhaps the most beautiful and direct connection lies in a concept known as electric-magnetic duality. This is a stunning mathematical symmetry that suggests a profound equivalence between electricity and magnetism at a fundamental level. In our everyday experience, they seem like partners, but distinct ones. Electric charges create electric fields, and moving electric charges create magnetic fields. But electric-magnetic duality proposes that this distinction is merely a matter of perspective. It suggests that the universe would look essentially the same if we could somehow swap the roles of all electric and magnetic phenomena. In this dual picture, what we call electrons could be seen as magnetic monopoles and vice versa. The equations of electromagnetism and even of more advanced theories would retain their form. It's as if the universe has a hidden toggle switch between its electric and magnetic personalities. For this breathtaking symmetry to be a true property of nature, magnetic monopoles must exist. You cannot have a perfect swap between electricity and magnetism if only one side of the partnership, the electric charge, has fundamental, isolated particles. The monopole is the missing actor required to complete this symmetrical pair, making the duality a real, physical symmetry rather than just an elegant mathematical curiosity. Think of it like a perfectly balanced scale. On one side, we have the entire world of electricity, with its positive and negative charges existing independently. On the other side, we have the world of magnetism, but as we currently know it, this side is lopsided. We only have inseparable dipoles, north and south, forever bound together. The scale is tilted, the symmetry is broken. The discovery of a magnetic monopole would be the weight that finally balances the other side of that scale. It would demonstrate that the universe does not favor electricity over magnetism. It treats them with a perfect, democratic equality at the most fundamental level. This electric-magnetic duality is so powerful that it extends its reach into the realm of quantum theory and even string theory, where it helps resolve apparent paradoxes and points the way toward a more unified understanding of all forces. The monopole, therefore, isn't just another particle to add to a list. It is the linchpin holding together one of the most profound symmetries physicists have ever conceived. This pursuit of symmetry also leads us to confront one of the greatest unsolved mysteries in physics, the matter-antimatter asymmetry of the universe. According to our best models, the Big Bang should have created equal amounts of matter and antimatter, which would have then annihilated each other in a flash of pure energy, leaving behind a cosmos filled with light and nothing else. And yet, here we are in a universe made almost entirely of matter. Something must have happened in the early universe to slightly favor matter over antimatter, a process known as baryogenesis. The mechanisms behind this are still not fully understood, but magnetic monopoles could have played a crucial role. In the frantic moments following the Big Bang, as the grand unified force was breaking and monopoles were condensing out of the cooling cosmos, their interactions could have provided the necessary conditions to violate the symmetry between matter and antimatter. The presence of these topological defects could have tilted the playing field, creating a slight excess of protons over antiprotons, of electrons over positrons. For every few billion annihilations, one matter particle would have been left over, and that tiny surplus is everything we see today. In this scenario, the very existence of galaxies, stars, planets, and life itself could be a direct consequence of processes involving magnetic monopoles in the first fleeting instants of time. Beyond these cosmic implications, the monopole's relationship with symmetry touches on the very nature of physical law. In mathematics, the structures that describe particles and forces are often tied to groups of symmetries. The grand unified theories that predict monopoles rely on specific, larger symmetry groups that encompass the smaller symmetries of the standard model. The process of symmetry breaking that forms a monopole is like a crystal forming from a liquid. The final structure has less symmetry than the initial, homogeneous state, but the defects that form the monopoles are themselves a frozen record of the original, higher symmetry. Studying a monopole would be like studying a single grain in a piece of wood to understand the entire tree's growth pattern. It would give us direct, experimental access to the symmetric laws that operated at energies 1,000,000,000,000 times greater than anything we can ever hope to reach with a particle collider. We would be holding a piece of the universe's original, perfect state, a relic that validates not just a single theory, but an entire approach to understanding reality through the elegant language of symmetry. This is why the hunt is so passionate and persistent. It is a direct test of our deepest intellectual striving to see the universe not as a collection of random rules, but as a manifestation of beautiful underlying order. To address the staggering overproduction of monopoles and their immense mass, theoretical physicists developed an even more ambitious extension to the grand unified framework, a concept known as supersymmetry. The core idea of supersymmetry is both simple and profound. It proposes a deep, fundamental symmetry between the two great families of elementary particles, the fermions, which are the building blocks of matter, like quarks and electrons, and the bosons, which are the force carriers, like photons and gluons. In a supersymmetric universe, every known particle would have a superpartner, a kind of cosmic shadow. For every matter particle, a fermion, there would be a force-carrying boson partner, and for every force carrier, a boson, there would be a matter fermion partner. An electron, a fermion, would be paired with a selectron, a boson. A photon, a boson, would be paired with a photino, a fermion. This elegant pairing would create a vastly more symmetric and stable theoretical structure, solving several nagging problems in particle physics at once. One of the most significant impacts of supersymmetry on the monopole story is how it dramatically alters the running of the fundamental force strengths. In the Standard Model, we can plot how the strengths of the electromagnetic, weak, and strong forces change as we go to higher and higher energies. In a simple grand unified theory, these three lines do not meet at a single precise point. They come close but miss each other, suggesting the unification is not quite perfect. But when you add supersymmetry into the equations, a minor miracle occurs. The presence of all the new superpartners modifies how these forces evolve with energy. When you replot the lines, they converge with stunning accuracy at a single grand unification energy point. This is one of the most compelling mathematical arguments for supersymmetry. It provides a beautiful and precise picture of how the three non-gravitational forces were once one. This more precise unification has direct and crucial consequences for the magnetic monopole. Because the grand unification scale is shifted to a slightly higher energy in supersymmetric theories, the mass of the predicted monopole also increases. While a traditional GUT monopole might have a mass of 10 to the 16 giga-electronvolts, a supersymmetric monopole could be even heavier, perhaps by an order of magnitude. This makes it even more impossible to create in a particle collider, but it also has a beneficial effect from a cosmological perspective. A heavier monopole would be produced less abundantly in the early universe, which naturally helps to alleviate the severity of the original monopole problem. It doesn't eliminate the need for cosmic inflation, but it makes the initial conditions before inflation somewhat less extreme, reducing the predicted relic density we would expect to find today and bringing theory more in line with our observational null results. Beyond its mass, supersymmetry also profoundly affects the monopole's stability and its interactions with matter. In many non-supersymmetric grand unified theories, the monopole is not completely stable. It can decay, albeit through processes that would take an unimaginably long time. Supersymmetry can introduce new mechanisms that stabilize the monopole further, making it a truly permanent feature of the cosmos. Furthermore, the spectrum of new particles predicted by supersymmetry opens up novel ways for a monopole to interact with ordinary matter. The process of proton decay catalysis, the Rubikov-Kalin effect, can be modified. new pathways for the decay could emerge, involving the superpartners of quarks and leptons, potentially changing the energy signature of the event. This means that if a monopole were detected, the specific details of how it catalyzes proton decay could provide direct evidence for or against supersymmetry, turning the monopole into a probe not just of grand unification, but of this larger symmetric framework as well. However, the story of supersymmetry in modern physics is one of brilliant promise meeting the hard reality of experimental data. For decades, supersymmetry was the leading candidate for physics beyond the Standard Model. It elegantly solved the hierarchy problem, which questions why the Higgs boson is so light compared to the immense Planck scale of gravity. It provided a compelling candidate for the universe's dark matter, as the lightest supersymmetric particle would be stable and could naturally account for the invisible mass holding galaxies together. And as we've seen, it made grand unification mathematically pristine. The physics community was optimistic that the Large Hadron Collider would soon discover a whole zoo of these superpartners. Yet, as the LHC collected more and more data at increasingly higher energies, no clear sign of supersymmetric particles emerged. The hoped-for electrons, photinos, and squarks remained stubbornly hidden. This non-discovery has forced a major re-evaluation. While supersymmetry as a theoretical concept is not ruled out, the simplest, most elegant versions of it, which predicted superpartners at masses low enough to be found at the LHC, are now highly disfavored. The theory has had to retreat to more complex and fine-tuned versions, where the superpartners are much heavier, pushing their discovery potential beyond the reach of our current colliders. This has clear implications for the monopole hunt. If supersymmetry exists but at a very high energy scale, then the monopoles it predicts would be even more massive and exponentially rarer than we first imagined. Our chances of finding one as a cosmic relic would become even slimmer. The ongoing search for supersymmetry and the search for magnetic monopoles are now deeply intertwined. The fate of one profoundly influences the prospects and predictions of the other. The continued absence of evidence for supersymmetry doesn't kill the theory, but it does push the entire paradigm, including its signature monopoles, into a more remote and challenging corner of theoretical physics, reminding us that the universe's deepest secrets are often guarded by layers of complexity we are only beginning to unravel. Beyond the solitary monopole, the universe's phase transitions might have woven even more intricate structures into the fabric of space-time. Structures where monopoles are not isolated knots but are tethered to cosmic threads, creating a network of unimaginable scale and energy. This brings us to the concept of cosmic strings, hypothetical one-dimensional defects that are, in essence, cracks in reality, and their profound connection to the magnetic monopoles we've been pursuing. If a monopole is a point-like kink in a field, a cosmic string is a line-like tear. Picture the universe's fields not as a smooth sheet but as a vast, complex tapestry. When the symmetry breaks, it's possible for the fields to arrange themselves in such a way that not just points, but entire lines of discontinuity form. These cosmic strings would be infinitesimally thin but possess immense density, with a thickness no wider than a proton but a mass per length that could be comparable to a mountain range crammed into every centimeter. They would stretch across the cosmos, potentially forming loops or infinite lines, and their gravitational influence would be so profound that they could act as gravitational lenses, warping the light from distant galaxies and seeding the formation of the earliest structures in the universe. The truly fascinating connection emerges in certain grand unified models where monopoles and cosmic strings are not independent entities but are intrinsically linked. In these scenarios, the symmetry breaking doesn't happen in one clean step but through a sequence of transitions. The first transition might create magnetic monopoles, as we've discussed. But then, as the universe cools further and undergoes a second symmetry breaking, the conditions can be such that the monopoles become connected by newly formed cosmic strings. Think of it like this: after the first freezing, you have a collection of point-like defects, the monopoles, scattered randomly. The second freezing then forces lines of high-energy tension to snap into existence between them, like cosmic rubber bands or incredibly taut wires linking the knots together. Each monopole would be attached to two strings, and each string would be terminated by a monopole at each end. This creates a vast, evolving network often called a necklace of monopoles and strings, a web of cosmic-scale energy drifting through the expanding universe. The cosmological implications of such a network are dramatic. A network of free-floating cosmic strings would oscillate wildly, and as strings intersect, they can chop off loops that gradually radiate away their energy as gravitational waves. But when monopoles are attached to the strings, the dynamics change completely. The monopoles act like heavy beads on a vibrating string, weighing it down and damping its oscillations. This monopole problem for strings, analogous to the original monopole overabundance issue, can suppress the production of gravitational waves from the string network. In some models, the monopoles can even cause the entire network to decay more rapidly. As the universe expands, the strings pull the monopoles apart, but the immense tension in the strings can eventually cause them to break, potentially releasing the monopoles back into the wild or annihilating them with antimonopoles on the same string. The evolution of this cosmic necklace becomes a complex ballet between the tension of the strings, the mass of the monopoles, and the expansion of the universe itself, a dance that would leave its imprint on the cosmos's background radiation and its gravitational wave background. This interconnected existence also offers a potential, albeit highly speculative, resolution to the monopole scarcity we observe. If a dense network of monopoles connected by strings formed in the early universe, the dynamics of that network could have efficiently annihilated monopoles with their antimonopole counterparts. Imagine two monopoles of opposite magnetic charge attached to the same long, vibrating string. As the string moves, it could eventually bring these two monopoles together, allowing them to annihilate in a tremendous burst of energy. This process could have acted as a cosmic-scale monopole disposal system, dramatically reducing their numbers to the sparse levels we infer today without requiring an inflationary epoch to do all the diluting. While inflation remains the favored solution, this alternative mechanism illustrates how the rich physics of topological defects provides multiple pathways to the universe we see, each with its own unique observational signatures. Perhaps the most extraordinary prediction involving these connected systems is a phenomenon known as the monopole string catalyzed proton decay. We've already discussed how a lone monopole can catalyze the decay of protons. But when a monopole is attached to a string, the effect can be amplified or altered. The cosmic string, a conduit of immense energy, could act as a channel, making the catalysis process even more efficient or extending its range. Furthermore, the motion of a monopole string system through space would be unlike anything else. A free monopole would plow through matter. A monopole tethered to a cosmic string, however, might be whipped around at incredible speeds as the string vibrates, or it could slowly sweep through a volume of space like a cosmic fishing line, its monopole hook catching and unraveling protons in a wider area. The detection signature for such a composite object would be unlike that of a solitary monopole, perhaps a series of correlated proton decay events spread out along a line in a massive detector, a pattern that would be unmistakably exotic. The search for evidence of cosmic strings with or without monopoles is an active field in cosmology. Astronomers scrutinize the cosmic microwave background for the telltale thin, linear scars that a passing string would leave in the temperature map. They also search for the gravitational waves that a decaying network of strings would produce, a stochastic background hum that might be detectable by future observatories like the Laser Interferometer Space Antenna, or LISA. Finding a cosmic string would be a discovery of Nobel Prize-winning magnitude in its own right. But if we were ever to find evidence that such strings are indeed adorned with magnetic monopoles, it would confirm one of the most specific and complex scenarios predicted by grand unification. It would provide a direct window into the sequential breaking of symmetries in the early universe, revealing not just that the forces unified, but the precise steps they took as they froze out into the distinct entities we know today. This interconnected web of defects represents the highest level of cosmic craftsmanship, a relic structure that encapsulates the dramatic history of the universe's birth in a way no single particle ever could. While grand unified theories paint a compelling picture of monopoles as point-like knots in the fabric of space-time, our quest to understand the universe's deepest workings leads us to an even more ambitious framework, string theory. This candidate for a theory of everything seeks to unify all forces, including gravity, by proposing that the fundamental constituents of reality are not zero-dimensional points but tiny, vibrating strings. In this radically different paradigm, the very nature of what a particle is undergoes a profound transformation, and with it, our understanding of the magnetic monopole evolves from a solitary knot into a higher dimensional, extended object. The monopole is no longer just a particle. Within string theory, it can manifest as a membrane, a soliton, or a dynamic surface known as a D-brane, revealing a landscape of magnetic structures far richer than anything conceived in traditional particle physics. The leap from points to strings is monumental. In the Standard Model and GUTS, particles are treated as infinitesimal dots, which leads to intractable mathematical infinities when gravity is brought into the quantum picture. String theory resolves this by replacing the point with a one-dimensional loop of string, so small that it appears point-like at our everyday scales. The different vibrational modes of this string, much like the various harmonics of a violin string, correspond to different particles. One vibration gives a photon, another an electron, and so on. Crucially, one of these vibrational patterns corresponds to the graviton, the hypothetical quantum carrier of gravity, thereby naturally weaving gravity into the quantum tapestry. This elegant shift in perspective forces us to reconsider all fundamental objects, and when we ask the question, what is a magnetic monopole in a universe made of strings? The answer requires us to explore the theory's full architectural landscape, which includes objects of multiple dimensions. This is where D-branes enter the story, and they are absolutely pivotal. A D-brane, short for Dirichlet membrane, is a surface where open strings can end. Think of our universe as a three-dimensional brane within a higher dimensional bulk space. Just as a point can be the end of a line, a D-brane can be the boundary where an open string terminates. Now consider electromagnetism. In string theory, the photon, the carrier of the electromagnetic force, is represented by a specific vibration of an open string whose endpoints are tied to a D-brane. The electric charge of a particle is then related to how these open strings attach to the brane. So, where does the magnetic monopole fit in? A magnetic monopole in string theory is not described by an open string, but by a higher dimensional D-brane itself. Specifically, a magnetic monopole can be a D-brane that has been wrapped around a compact, curled-up dimension of space. From our perspective in the three extended dimensions we experience, this wrapped brane looks like a point-like object, but it inherently possesses the topological properties of a solitary magnetic charge. To grasp this abstract idea, imagine a garden hose. From a distance, it looks like a one-dimensional line. But if you look very closely, you see that the hose has a two-dimensional surface, its length and its circumference. Now, imagine that one of the extra dimensions predicted by string theory is curled up into a tiny circle like the hose's circumference. A fundamental string itself is one-dimensional. But a D2 brane is a two-dimensional surface. If you take this two-dimensional brane and wrap it tightly around the circular dimension, that dimension becomes hidden from our view. What we perceive is only the remaining one-dimensional length of the object, which now appears as a point-like particle in our three-dimensional space. This wrapped brane is a solitonic object, a stable, particle-like lump of energy, and its properties precisely match those of a magnetic monopole. It carries the correct magnetic charge and interacts with the photonic open strings in exactly the way Maxwell's equations demand for a monopole. In this picture, electric charge and magnetic charge are not just symmetrical. They arise from fundamentally different types of objects in the string-theoretic landscape: electric charges from open strings and magnetic charges from wrapped d-branes. This string-theoretic perspective offers several stunning advantages over the traditional grand unified theory approach. First, it provides a natural and robust existence proof for monopoles. In GUTS, monopoles are stable because of topological reasons, but their exact properties depend on the specific symmetry group one chooses for unification. In string theory, the existence of monopoles is almost inevitable given the presence of d-branes and compactified dimensions. They are baked into the geometry of the universe. Their stability is guaranteed by the conservation of a certain brane charge, which is a direct analog of the topological charge in GUTS but is even more fundamental. Second, string theory elegantly explains the Dirac quantization condition, the deep link between the quantization of electric charge and the existence of magnetic monopoles. In the string picture, the quantization of electric charge arises from the fact that open strings can only end on d-branes in discrete ways. The magnetic charge of a wrapped brane is also quantized by the geometry of the compact dimension it wraps. The beautiful interplay between these two quantization conditions automatically yields Dirac's famous formula, showing that this quantum rule is not a mere consistency condition but a direct consequence of the universe's underlying geometry. Furthermore, string theory provides a concrete and calculable framework for understanding the immense mass of a grand unified monopole. In GUTS, the mass is tied to the unification scale, a number that is put into the theory by hand based on the running of the force strengths. In string theory, the mass of a monopole is determined by the tension of the d-brane and the volume of the compact dimension it wraps. The tension of a d-brane is a fundamental parameter in the theory, and the volume of the compact dimensions is set by the vacuum state of the universe. This means that the monopole's mass, while still astronomically large, is calculable from first principles if we ever determine the specific geometry of the string theory vacuum that describes our world. This shifts the monopole from being a parameter-dependent prediction to a geometrical inevitability, its properties locked in by the shape of the hidden dimensions. However, this power comes with a significant challenge: the landscape of possibilities. String theory does not uniquely predict a single set of physical laws, but rather a vast landscape of perhaps 10 to the 500 possible stable vacuum configurations, each with different compactified geometries, different forces, and different particle content. In most of these vacua, monopoles of the GUT type will exist, but their precise masses and interaction strengths could vary dramatically. This makes it difficult to make a single, sharp, testable prediction that would definitively confirm the string-theoretic monopole over a GUT one. Both frameworks predict a heavy, stable, topologically protected object with a quantized magnetic charge. The true distinction lies in their origin story. One is a knot in a field, the other a wrapped membrane in a higher dimensional space. For an experimentalist who might one day find a monopole in a detector, it could be extremely challenging to discern which theoretical origin story is correct, as both would manifest with nearly identical signatures in terms of their magnetic charge and their ability to catalyze proton decay. The discovery would validate the necessity of a deep unified theory, but untangling whether that theory is a four-dimensional GUT or a 10-dimensional string theory would require probing details of the monopole's structure and interactions that may be forever beyond our reach, leaving us with a magnificent discovery that points the way forward while still guarding the ultimate secrets of cosmos. Despite the elegant and compelling case for magnetic monopoles within grand unified theories, the persistent failure to detect even a single one has forced the theoretical physics community to confront some hard questions. This has sparked a vibrant, ongoing debate, leading to serious criticisms of the standard GUT picture and the exploration of alternative models that either avoid monopoles altogether or reimagine their fundamental nature. One of the most significant challenges is simply the sheer longevity and scale of the null results. Decades of increasingly sophisticated searches, from deep underground laboratories to cosmic ray detectors and particle colliders, have all come up empty. This consistent absence places ever tighter constraints on the possible properties and abundance of these particles. For a theory to remain viable, its predictions must eventually find some experimental footing, and the monopole's continued status as a ghost is a source of genuine tension. It forces theorists to ask, is the problem with our experiments, or is it with the theories themselves? A major area of scrutiny involves the initial conditions and specific mechanics of the grand unification phase transition. The canonical story of domain formation and topological defect creation relies on specific assumptions about how the early universe cooled. Critics point out that this process is not as straightforward as the simple freezing pond analogy might suggest. The transition might not have been a clean, instantaneous break, but a smoother crossover transition. In such a scenario, the universe wouldn't have formed distinct, misaligned domains with sharp boundaries. Instead, the symmetry would have broken in a more coordinated, homogeneous fashion across space, effectively preventing the formation of the topological knots that become monopoles. Furthermore, the initial state of the universe before the transition is a realm of pure speculation. If there was significant pre-existing disorder, or if quantum fluctuations played a different role, the entire mechanism for monopole production could have been suppressed or altered beyond recognition. The elegance of the topological argument, while powerful, depends entirely on the universe following a very specific and idealized script in its first moments, a script that may not reflect the messy, quantum gravitational reality of the Big Bang. This leads directly to alternative frameworks that seek to achieve the goal of unification without the cosmological baggage of a monopole overdose. One prominent class of alternatives involves theories with a different, more complex symmetry-breaking pattern. Instead of a single, dramatic transition from a grand unified group directly down to the standard model forces, some models propose a cascading series of smaller, intermediate steps. In these scenarios, the symmetry breaks in a sequence through several gauge groups. The specific pathway chosen can have a dramatic effect on the types of topological defects that are allowed to form. Certain pathways are monopole-free, meaning the topology of the vacuum manifold after the final symmetry breaking does not support the existence of stable point-like defects. It's like finding an alternative route to the same destination that cleverly avoids a treacherous mountain pass. You still get to unify the forces, but you bypass the dangerous terrain that would have forced you to create monopoles along the way. Another radical alternative that has gained significant traction is the idea that our universe is not fundamentally four-dimensional at all. In brain-world scenarios which emerge from string theory, our observable universe is a three-dimensional brain embedded within a higher dimensional bulk space. In this picture, the standard model particles, including photons and electrons, are constrained to move only within our brain, like characters trapped on the surface of a movie screen. Gravity, however, can leak out into the extra dimensions. This setup can elegantly solve the monopole problem. If the grand unified gauge fields are also confined to our brain, but the mechanism for monopole formation requires access to the full bulk geometry, the creation of stable monopoles might be impossible or highly suppressed. The topological conditions necessary for their existence simply wouldn't be met in the lower dimensional reality we inhabit. In such a universe, the profound symmetry between electricity and magnetism might be a hidden feature of the full higher dimensional theory, but it would not manifest in our world as a free, point-like magnetic charge. This provides a neat, though speculative, escape clause from the monopole prediction. The debate is further fueled by the ambiguous status of supersymmetry. As we discussed, supersymmetry made grand unification mathematically pristine and offered a compelling dark matter candidate. For decades, it was the best motivated and most popular extension of the Standard Model, and its framework naturally accommodated heavy, stable monopoles. However, the continued non-discovery of supersymmetric particles at the Large Hadron Collider has cast a long shadow. While not ruled out entirely, the simplest and most elegant versions of supersymmetry are now severely constrained. This has a direct knock-on effect for monopole searches. If supersymmetry is realized in nature at a very high, inaccessible energy scale, then the monopoles it predicts would be even more massive and exponentially rarer. The already slim chance of detecting a relic monopole becomes almost infinitesimal. Some physicists argue that the lack of evidence for supersymmetry weakens the entire case for a traditional GUT monopole, as the most beautiful and natural theoretical home for them is now looking less likely. This has pushed the community to consider even more exotic possibilities, such as composite models where what we think of as a monopole is not a fundamental particle, but a bound state of other objects, potentially with different, subtler detection signatures. This vibrant theoretical landscape, filled with competing ideas and critiques, is not a sign of weakness but a testament to the health and rigor of fundamental physics. The monopole is a powerful theoretical lodestone, forcing us to refine our ideas and consider every possible angle. The ongoing debate centers on a fundamental question: is the universe's mathematical beauty most perfectly expressed in the form of grand unified theories that demand monopoles, or is its beauty of a different, more subtle kind, one that cleverly avoids such particles while still achieving unification? The null results from experiments are not merely failures, they are valuable data points that guide theorists away from dead ends and toward more promising avenues. They tell us that if monopoles exist, their properties and abundance must lie within a very narrow and exotic window, a window that is being systematically closed by both experimental ingenuity and theoretical creativity. This process of challenge and response is the engine of scientific progress, ensuring that our journey toward understanding the cosmos remains dynamic, critical, and endlessly fascinating. Given the colossal energy needed to create a grand unified monopole, a feat far beyond any machine we have today, the question naturally arises: where do we go from here? The hunt is far from over. It is evolving, shifting from a hope of creation to a refined search for relics, leveraging a new generation of instruments of breathtaking scale and sensitivity. The next chapter in this century-long quest will be written by future colliders and observatories, machines designed not just to find what we expect, but to probe the unknown with an audacity that pushes the very boundaries of engineering. One of the most ambitious projects on the drawing board is the Future Circular Collider, or FCC. Envisioned to be built in a new underground tunnel circling nearly 100 kilometers in circumference beneath the French and Swiss countryside, the FCC would be a monumental leap beyond the Large Hadron Collider. Its primary goal is to study the Higgs boson with exquisite precision and search for new particles at higher energy frontiers. While its planned collision energy of 100 tera-electronvolts is still a universe away from the 10 to the 16 needed to produce a GUT monopole from scratch, its sheer intensity opens a different, more subtle window. The FCC wouldn't aim to manufacture a monopole in a single, thunderous collision. Instead, it would produce an astronomical number of collisions, quintillions of proton-on-proton impacts, creating a fire hose of data. Within this unimaginably vast dataset, physicists would search for the fingerprints of virtual monopoles. In quantum field theory, even processes that are forbidden from happening outright can still leave a faint statistical imprint on the outcomes of lower energy events through so-called quantum loops. The incredibly precise measurements of the FCC could reveal tiny deviations in scattering cross-sections or rare decay rates that would point unambiguously to the existence of very heavy, otherwise inaccessible particles like magnetic monopoles. It's a search for the shadow of the particle, a ghostly influence on the world we can see, hinting at the massive object lurking just beyond our direct reach. Beyond the energy frontier, the intensity frontier offers another promising path. While we cannot reach the monopole's mass energy, we might be able to exploit a quantum trick to pair-produce them. According to the theory, the energy required to create a monopole-antimonopole pair can be significantly lowered in the presence of an incredibly strong magnetic field. Future colliders or dedicated experiments could potentially generate the strongest magnetic fields ever created in a laboratory, effectively catalyzing the pair production of these particles at energies below their nominal rest mass. Imagine using a powerful electromagnetic cannon to fire a particle into an immense, contained magnetic field, a field so strong it warps the vacuum of space itself, momentarily making it energetically favorable for a monopole and its opposite to pop into existence. This is not just theoretical speculation, it's a concrete proposal being studied for next-generation facilities. Detecting such an event would require specialized detectors surrounding the interaction point, instruments designed to catch the unique, high ionization tracks of these massive, slowly moving objects as they emerge from the collision point. The FCC collaboration is already considering such specialized sub-detectors, ensuring that even if the monopole hides from the main physics programs, a dedicated trap will be waiting. The search extends far beyond the confines of terrestrial tunnels, reaching out into the cosmos with next-generation cosmic ray observatories. Experiments like the Pierre Auger Observatory in Argentina and the Telescope Array in the United States monitor vast swaths of the sky, watching for the extensive air showers produced when ultra-high-energy cosmic rays strike the atmosphere. While these observatories have placed stringent limits on the flux of super-heavy, relativistic monopoles, their successors are being planned with even greater sensitivity. The proposed Giant Radio Array for Neutrino Detection, or GRAND, envisions 200,000 radio antennas spread over 200,000 square kilometers, making it an incredibly sensitive ear tuned to the universe's most energetic messengers. A magnetic monopole, due to its immense mass and magnetic charge, would interact with the galactic magnetic fields in unique ways, potentially being accelerated or deflected along its journey. If a relic monopole were to streak through the Earth's atmosphere, it would produce a very distinctive, deeply penetrating air shower, one that starts higher up and develops more gradually than a shower from a proton or atomic nucleus. GRAND's immense coverage and its ability to detect the radio pulses from these showers would give it an unprecedented chance to spot these rare, cannonball-like particles, effectively turning a significant portion of the Earth's surface into a monopole detector. Simultaneously, the indirect search continues to grow in sophistication. As we enter the era of multi-messenger astronomy, where we observe the cosmos using light, gravitational waves, and neutrinos simultaneously, we gain new tools to hunt for the environmental impact of monopoles. The next generation of gravitational wave observatories, like the Laser Interferometer Space Antenna, or LISA, will open a low-frequency window onto the universe. LISA could potentially detect the gravitational waves emitted by cosmic strings as they vibrate and intersect. As we discussed, some models inextricably link monopoles to these strings. The specific spectral signature of a network of strings with heavy monopoles attached to them would be different from a network of free strings. If LIS were to detect gravitational waves from cosmic strings, the detailed properties of that signal could indicate whether monopoles are present, acting as the beads on a cosmic necklace. Furthermore, as our catalogues of neutron stars grow with telescopes like the James Webb Space Telescope and the upcoming Vera-C Rubin Observatory, astronomers will be able to conduct systematic studies of their thermal properties. Finding a population of unexpectedly warm, ancient neutron stars for which no other heating mechanism is apparent would strengthen the case that a hidden population of monopoles is at work within them, catalyzing proton decay and providing a steady internal heat source. The persistent absence of a detection, despite all these heroic efforts, is itself a powerful scientific result. Each new experiment that fails to find a monopole places a stricter upper limit on their possible abundance in the universe. These limits continuously shape and constrain our theoretical models. They tell theorists that if monopoles exist, they must be even rarer, heavier, or interact more weakly than we had previously imagined. This feedback loop between theory and experiment is the engine of scientific progress. It forces the invention of ever more creative detection strategies and pushes the development of technologies that were once the realm of pure science fiction. The quest for the magnetic monopole, therefore, is more than a single experiment. It is a long-term, global program that drives innovation across physics, from the deepest depths of the Earth to the farthest reaches of space, all in pursuit of a deeper understanding of the symmetries that underpin our reality. Beyond the intricate detectors and advanced theoretical equations, the magnetic monopole possesses a unique and powerful quality that makes it a superstar for science education and public outreach. Its story is a perfect narrative vessel for conveying the essence of the scientific method, not as a dry list of steps in a textbook, but as a dynamic, human, and often thrilling detective story. Think about it. You start with a simple, almost childlike observation. Why do magnets always have two poles? This is a question that can captivate a classroom of fifth graders just as easily as it once captivated the genius of Paul Dirac. From that simple, curious starting point, the journey unfolds, demonstrating how scientists take a basic observation and use it to ask a profound what-if question. What if a solitary pole could exist? This single question then blossoms into a rich tapestry of theoretical prediction, mathematical derivation, and decades of persistent experimental ingenuity. The monopole quest showcases science not as a static collection of facts, but as a living, breathing process of inquiry. Educators can use this narrative to illustrate every stage of the scientific process in a compelling way. The initial observation is the asymmetry in Maxwell's equations. The hypothesis is Dirac's brilliant insight that a monopole would explain charge quantization. The prediction phase is spectacular, with grand unified theories not just suggesting but demanding the particle's existence and even forecasting its staggering properties. Then comes the testing phase, which is a story in itself, filled with ingenious experiments from induction coils in deep labs to plastic track detectors in space. And crucially, the story includes the null results, the decades of not finding anything. This is a vital, often overlooked lesson for students. Science isn't just about triumphant eureka moments, it's about perseverance in the face of mystery. A null result isn't a failure, it's data that tells us our models might need refinement, that the universe is more subtle than we imagined, or that we simply need to look harder and smarter. The ongoing hunt for the monopole is a masterclass in intellectual humility and tenacity. Furthermore, the topic serves as a magnificent bridge, connecting seemingly disparate fields of science into a cohesive picture. A lesson on magnetic monopoles can effortlessly flow from classical electromagnetism to quantum mechanics, then to particle physics and cosmology, touching upon the Big Bang, cosmic inflation, and even the potential fate of protons. It shows students that physics isn't a series of isolated units to be memorized for a test, but an interconnected web of knowledge where an idea from the 1860s can directly inform our understanding of the universe's first second of existence. For a young person wondering why they need to learn algebra or calculus, the monopole provides a stunning answer. Dirac's quantization condition is a beautiful piece of mathematics that directly leads to a testable physical prediction. It demonstrates that math is not just an abstract game, but the very language the universe is written in, a language that allows us to predict the behavior of reality itself. The aspirational power of this quest cannot be overstated. The idea of hunting for a fossil from the birth of the cosmos, a particle that could rewrite textbooks and unlock new technologies, is the stuff of scientific legend. It captures the imagination in a way that rote memorization never can. Outreach programs at universities and science centers often use topics like this to spark that initial flame of wonder. Imagine a planetarium show that doesn't just show the constellations, but tells the story of how we are using the entire cosmos as a laboratory, searching for clues in ancient starlight and the warmth of neutron stars. The monopole represents the ultimate treasure hunt, one that requires not shovels and maps, but colossal intellect and even more colossal machines. It makes the career of a physicist feel like that of an explorer or a detective, someone on the front lines of deciphering the greatest mystery of all. This story also beautifully humanizes science. It's a tale of individuals, from the lone theorist like Dirac having a flash of insight, to experimentalists like Blas Cabrera spending years perfecting a single, delicate instrument, to the massive global collaborations like Mo Edel at CERN involving thousands of people. It shows that science is a communal, cumulative effort where each generation stands on the shoulders of the last. The Valentine's Day Monopole event is a perfect anecdote for this, a moment of high drama and excitement, followed by the sobering, rigorous requirement of replication. It teaches that in science, extraordinary claims require extraordinary evidence, and that a single data point, no matter how perfect, is not enough. This is a profound lesson in critical thinking, applicable far beyond the walls of a physics lab. Ultimately, the magnetic monopole, even in its current state of elusive mystery, is a powerful catalyst for curiosity. It encourages people to look at the ordinary world, a simple refrigerator magnet, and ask extraordinary questions about the fundamental nature of reality. It demonstrates that at the frontiers of knowledge, our understanding is provisional, and that the biggest discoveries might still be waiting just beyond our current grasp. By sharing this ongoing saga with students and the public, we don't just transmit information, we invite them to become part of the story themselves, to feel the excitement of not knowing and the profound drive to find out. In this way, the search for a solitary magnetic charge does more than just probe the early universe. It helps ensure that the next generation of minds will be ready to continue the search, armed with curiosity, rigor, and an unshakable sense of wonder. Yet the magnetic monopole is far more than just a subject for scientific journals and laboratory experiments. It has also captured the creative imagination, making its way into the worlds of science fiction, film, and literature, where its speculative potential is unleashed. These portrayals, while often taking significant artistic license, play a fascinating role in shaping how the public perceives this elusive concept, and can even serve as a surprising catalyst, sparking genuine scientific interest in a new generation of thinkers. When a writer or filmmaker needs a piece of credible-sounding, futuristic technology or a mysterious cosmic phenomenon, the monopole often fits the bill perfectly. Its basis in real theoretical physics gives it a veneer of plausibility that pure fantasy elements lack, allowing creators to build stories that feel grounded in possibility while exploring the furthest reaches of the imagination. This dance between fact and fiction creates a unique feedback loop where abstract scientific ideas are translated into narrative drama, and that drama, in turn, fuels curiosity about the underlying science. One of the most famous and direct incorporations of the monopole into popular culture is in the landmark 2001 science fiction film, The Core. In the movie, the Earth's core has stopped rotating, and a team of intrepid scientists must journey to the center of the planet to restart it with a series of nuclear detonations. Their vessel, the Virgil, is protected from the immense heat and pressure by a fictional material called unobtainium. But the key to their entire mission is their power source and navigational system, a device called a laser-powered magnetic monopole propulsion system. The characters explicitly state that they are using monopoles to generate an incredibly powerful magnetic field, which both propels the ship and creates a protective bubble. While the physics of surviving a trip to the Earth's core is wildly exaggerated, the film's writers did their homework by tapping into a real, albeit speculative, concept. They presented the monopole not as magic, but as a revolutionary, albeit poorly understood, piece of technology, giving audiences a tangible, if fictional, answer to the question, what could we do with one of these things? For many viewers, this was their first, and perhaps only, exposure to the idea of a magnetic monopole, planting a seed that combined scientific wonder with cinematic spectacle. Literature, particularly the genre of hard science fiction, has often delved even deeper, using monopoles not just as a plot device but as a central pillar for exploring profound philosophical and physical questions. The renowned author Larry Niven, in his Known Space series of stories and novels, frequently featured monopoles. In his fictional universe, monopoles are mined from the magnetic fields of planets and are a cornerstone of advanced technology. Niven's monopoles are treated as a valuable, dangerous, and physically plausible substance. He explores the consequences of their existence with a scientist's rigor, considering how their immense density and magnetic charge would affect everything from weapons to propulsion. Another powerful example is Greg Egan's Child's Ladder, a novel that pushes the boundaries of theoretical physics to their limits. While not solely about monopoles, Egan's work is steeped in complex ideas from quantum gravity and topology, the very fields that give rise to the monopole concept in real-world theories. Authors like Egan don't just name-drop the particle, they build entire narratives around the implications of its existence, challenging readers to engage with the same high-level concepts that professional physicists debate. This kind of storytelling does more than entertain. It educates and inspires by demanding a higher level of intellectual engagement from its audience. The influence of these fictional portrayals on public perception is a double-edged sword. On one hand, they bring an incredibly niche and complex scientific idea into the mainstream, demystifying the jargon and presenting it as something exciting and consequential. A viewer who enjoyed The Core might later stumble upon an article about real monopole searches and have a moment of recognition, a connection that makes the actual science feel more accessible and less intimidating. This is an invaluable service, breaking down the walls between the academic world and the general public. It fosters a culture that values and is curious about fundamental research, even if it doesn't have an immediate, obvious application. The dramatic potential of the monopole, a particle that could unravel matter or power starships, makes theoretical physics feel heroic and adventurous, attracting young minds to the field who were first captivated by its fictionalized version. On the other hand, these representations can also create misconceptions. The monopole in a film is often a fully understood and engineered technology, its properties tailored to the needs of the plot. This can lead to an oversimplified view of the scientific process. In reality, the search is painstaking, slow, and fraught with uncertainty. It is not a simple matter of retrieving a known substance to solve a clear-cut problem. The fictional monopole often works with a reliability and power that far exceeds even the most optimistic theoretical predictions for a real one. This can create a gap between the exciting sci-fi concept and the more nuanced, challenging reality that scientists face. The key for science communicators is to bridge this gap, using the public's familiarity with the fictional concept as a starting point for a deeper conversation about the true nature of the search, the evidence, and the profound questions that remain unanswered. Perhaps the most significant impact of these cultural representations is their power to inspire real scientific curiosity. There are countless anecdotes of scientists and engineers who credit their career path to a pivotal moment in their youth, reading a compelling science fiction novel or watching a mind-expanding film. A story that features a magnetic monopole in a thoughtful way introduces a young reader to concepts like symmetry breaking, topology, and grand unification long before they encounter them in a classroom. It presents these ideas not as dry facts to be memorized, but as puzzles to be solved, as keys to unlocking the secrets of the universe. This narrative framing is incredibly powerful. It encourages a mode of thinking that is essential for a scientist, the ability to ask what if, and to follow the logical consequences of an idea, no matter how strange it may seem. The fictional monopole becomes a mental model, a tool for exercising the imagination in a way that is directly applicable to theoretical physics. This inspirational effect isn't just a happy accident, it's a testament to the shared territory between science and science fiction. Both are fundamentally concerned with exploring possibilities. The scientist asks, could a magnetic monopole exist based on the laws of physics, and then sets out to test that hypothesis through observation and experiment. The science fiction author asks, if magnetic monopoles did exist, how would that change our world, our technology, and our place in the universe, and then builds a narrative to explore those implications. These are two sides of the same coin. The author's speculative exploration can sometimes even precede and influence the scientific one, proposing applications or consequences that hadn't occurred to researchers. While a novelist's specific technological vision may not be blueprinted for reality, the act of imagining it expands the realm of the possible and encourages everyone, scientists included, to think more boldly about the future. Ultimately, the journey of the magnetic monopole from the pages of Dirac's papers to the silver screen and science fiction masterpieces highlights a beautiful synergy between different ways of understanding our world. The rigorous, evidence-based pursuit of science provides the foundation and the rules of the game. The creative, narrative-driven world of art and literature then takes those rules and plays with them, exploring their human and dramatic potential. This cultural conversation ensures that the most profound questions of physics don't remain locked away in ivory towers but resonate through our shared stories and myths. The continued presence of the monopole in our popular culture is a sign of its enduring power as a symbol of nature's hidden symmetries, humanity's relentless curiosity, and the thrilling, unending quest to understand the fundamental architecture of everything that exists. The profound implications of discovering a magnetic monopole extend far beyond the laboratory, forcing us to confront a new set of ethical and societal questions that would arise from such a fundamental shift in our understanding of reality. Imagine a world where we could, for the first time, isolate a pure magnetic charge. The initial scientific euphoria would be quickly tempered by a more sobering realization. This particle, a messenger from the universe's birth, could become one of the most powerful and dangerous substances ever known. Its potential applications would almost certainly fall into the category of dual-use technology, a term used to describe research or innovation that can be applied for both profoundly beneficial and deeply destructive purposes. On one hand, a monopole could unlock clean, limitless energy, revolutionize computing, and open new frontiers in medicine. On the other, it could enable weapons of unprecedented power and create entirely new vectors for global instability. The same fundamental property that makes it so exciting, its ability to catalyze proton decay, is also what makes it a potential doomsday device. The power to unravel the very fabric of matter is the ultimate dual-use capability, and its emergence would demand a global conversation about responsibility, control, and the very future we wish to build. This dichotomy is starkly illustrated by the energy prospects. A single monopole could, in theory, act as the core of a microscopic reactor, transforming common hydrogen into pure energy through catalyzed proton decay. The energy density would be millions of times greater than nuclear fission or fusion, offering a potential solution to humanity's energy crisis and a path away from fossil fuels. It could power cities for centuries with a fuel source as abundant as seawater. Yet this same mechanism, if weaponized, could create an entirely new class of armament. A device designed not to fission or fuse atoms, but to simply initiate the decay of stable matter in a chain reaction, could have a destructive potential that dwarfs our current nuclear arsenal. It would be a bomb with no radioactive fallout in the traditional sense, but one that could, in a worst-case scenario, threaten to render a continent or even the entire planet uninhabitable by converting its mass into a firestorm of radiation. The geopolitical scramble to control such a resource would be immense, potentially triggering a new kind of arms race far more perilous than the nuclear standoff of the 20th century. The nation or entity that first mastered monopole technology would possess a strategic advantage so overwhelming it could destabilize the entire international order. Beyond weaponry, the societal adaptation to this new physics would be profound and disorienting. Our entire technological civilization is built upon a set of physical laws we believed were fixed and immutable. The discovery of a magnetic monopole would not just add a new particle to a chart, it would shatter a foundational pillar of classical physics, demonstrating that a symmetry we considered absolute is in fact broken in our current universe. The public's trust in science, which is often based on the perception of settled facts, could be shaken. We would have to collectively come to terms with the idea that the stability of the atoms that constitute our bodies and our world is not an absolute guarantee, but a conditional state that depends on the extreme rarity of these particles. This introduces a subtle but powerful philosophical shift, moving us from a universe of certainties to one of cosmic contingencies. Educational systems would need to be overhauled, textbooks rewritten from the ground up, and a massive public information campaign would be necessary to explain this new reality without causing undue alarm or fostering misinformation. The economic disruption would be equally seismic. Consider the potential of magnetricity, the flow of magnetic charge. If harnessed, it could render our entire electrical grid, with its resistive losses and massive infrastructure, obsolete. The trillion-dollar industries built around generating and transmitting electricity could face extinction almost overnight. While this promises a future of near-perfect efficiency, the transition would be economically catastrophic for millions of workers and entire nations whose economies are tied to legacy energy systems. The companies and countries that control the source of monopoles, whether found as natural relics or eventually synthesized, would wield economic power comparable to the oil empires of the past, but concentrated in a resource far more potent and rare. This could create staggering new inequalities, a world divided between those with access to monopole-based technology and those left behind in a pre-monopole age. The ethical imperative would be to manage this transition justly, ensuring that such a revolutionary technology benefits all of humanity and does not become a tool for entrenching power and wealth in the hands of a tiny minority. Navigating this new landscape would require the creation of entirely new legal and regulatory frameworks, something for which there is no precedent. How do you govern a substance that is both a fundamental component of reality and a weapon of mass destruction? International treaties akin to the Non-Proliferation Treaty would need to be drafted and ratified, but with even greater urgency and stringency. The very concept of arms control would have to be redefined to include the control of a single particle type. Research into monopole physics would likely have to be conducted under conditions of extreme secrecy and security, raising difficult questions about scientific transparency and the free exchange of ideas that has traditionally driven fundamental research. Do we classify the most basic research into the nature of our universe? The tension between the scientific ideal of open inquiry and the pragmatic need for global security would become one of the defining ethical challenges of the age. Furthermore, the long-term environmental impact of monopole use is completely unknown. While a monopole reactor would not produce greenhouse gases, the waste products of catalyzed proton decay would include intense bursts of gamma radiation and other high-energy particles, presenting a novel and potentially intractable nuclear waste problem that could persist for generations. Ultimately, the discovery of the magnetic monopole would hold up a mirror to humanity itself. It would test our collective maturity, our wisdom, and our capacity for foresight. This tiny particle would present us with a clear choice. Would we use this deeper understanding of cosmic symmetry to elevate our civilization, to solve our most pressing problems, and to reach for the stars? Or would we succumb to fear, short-sightedness, and old patterns of conflict, turning the key to the universe's first moments into a tool for our own destruction? The history of technological progress is a mixed bag, filled with both miraculous advances and terrible misapplications. The monopole, however, sits in a category of its own because it touches on the fundamental stability of matter. Its ethical weight is immense. The very act of searching for it is an expression of our deepest curiosity, but finding it would confer a responsibility unlike any we have faced before. It would demand a new era of global cooperation, a renewed commitment to peaceful applications of science, and a profound humility in the face of a universe that is far more strange, powerful, and delicate than we ever imagined. This quest for the magnetic monopole is a brilliant example of how the pursuit of a single, fundamental question can shatter the artificial barriers between scientific disciplines, creating a vibrant and collaborative ecosystem that spans the entire scale of reality. The search doesn't just live in one lab or one theory. It connects the cosmologist peering at the afterglow of the Big Bang with the particle physicist analyzing collisions at CERN. And surprisingly, it also involves the materials scientist working with exotic crystals at temperatures near absolute zero. This is not a series of parallel, isolated investigations. It is a deeply interconnected web where a discovery in one field can send ripples through all the others, accelerating progress in a way that siloed research never could. The connection between cosmology and particle physics is perhaps the most profound. Cosmologists provide the grand stage, the story of the universe's evolution, its expansion, cooling, and the phase transitions that shaped its laws. They look at the large-scale structure of the cosmos, the precise patterns in the cosmic microwave background, and the very fact that the universe is old and largely empty, and they ask, what does this tell us about the particles that must have existed in the first moments? The cosmological monopole problem was a direct challenge thrown down by cosmologists to the particle physicists. Your beautiful grand unified theories predict a universe that should have collapsed under the weight of its own monopoles. Explain this or your theories are wrong. This challenge was the direct catalyst for the theory of cosmic inflation, a cosmological idea that then became a cornerstone of modern particle physics. Now, particle physicists designing experiments use cosmological data to set limits on the possible mass and density of relic monopoles. If the cosmology says they must be incredibly rare, then the particle detectors must be correspondingly larger and more sensitive, or we must look for more clever, indirect signatures. This feedback loop is essential. Cosmology tells the particle hunters where and how to look, refining the search strategy with every new observation of the distant universe. On the other end of the scale, the world of condensed matter physics has provided an unexpected and incredibly fertile testing ground for these high-energy concepts. The discovery of emergent monopoles in spin ices was a watershed moment. For decades, the magnetic monopole was a purely theoretical construct, a ghost from the high-energy past. But in the lab, physicists found a system where these ghostly particles came to life, not as fundamental entities but as collective excitations. This was not just a cute analogy, it was a full-blown quantum simulation. The mathematical equations describing the interactions and dynamics of these emergent monopoles in the crystal lattice are formally analogous to those describing their cosmic counterparts. This means that a materials scientist in a lab can effectively perform experiments on monopole physics by applying magnetic fields, changing temperatures, and measuring the resulting magnetic currents in a spin ice. They can test how these quasi-particles form, move, and interact, providing tangible data that feeds back into the theoretical models used by cosmologists and particle physicists. A prediction about how a cosmic monopole might catalyze a reaction could be inspired by observing how an emergent monopole facilitates a magnetic relaxation process in a crystal. This transforms an inaccessible, cosmic-scale phenomenon into a tabletop experiment, dramatically accelerating our understanding. This interdisciplinary cross-pollination is powered by a shared language and a shared set of powerful tools, chief among them being the mathematics of topology. Whether you're a cosmologist modeling the formation of defects in the early universe, a particle physicist calculating the stability of a soliton, or a condensed matter physicist mapping the magnetic structure of a frustrated magnet, you are likely using the same topological concepts. Ideas like homotopy groups, which classify the types of stable defects that can form when a symmetry breaks, are universal. A cosmologist uses them to predict whether a phase transition will produce monopoles, cosmic strings, or domain walls. A condensed matter physicist uses the exact same mathematics to explain why a particular defect in a crystal, like a dislocation or a skymion, is topologically protected and thus stable. This common mathematical foundation allows researchers from seemingly unrelated fields to understand each other's work deeply and to recognize that a breakthrough in one area might solve a stubborn problem in another. A new way of calculating the energy of a topological defect in a superconductor might provide the key to understanding the evolution of a network of cosmic strings in the early universe. The collaborative efforts themselves are as varied as the fields involved. Large-scale particle detectors like MOEDL at CERN are inherently interdisciplinary, bringing together experts in detector design, nuclear physics, materials science for the track-edge detectors, and data analysis to distinguish a potential monopole signal from background noise. Meanwhile, teams studying ancient mica or deep-sea nodules combine the skills of geologists who understand the formation and history of the materials with nuclear physicists who can identify the unique signatures of a monopole's passage. In laboratories studying spin ices, collaborations form between solid-state chemists who synthesize the perfect crystals, experimental physicists who perform the ultrasensitive magnetic and thermal measurements, and theoretical physicists who interpret the data using models borrowed from high-energy theory. These partnerships are not always easy. They require scientists to step outside their comfort zones and learn the jargon and conventions of another field. But the payoff is immense. The condensed matter physicist might not be an expert on grand unification, but they can ask a crucial question that the particle theorist had never considered. What if the monopoles interaction is screened in this specific way? This outside perspective can break a logjam and open up entirely new avenues for both theory and experiment. Ultimately, this interdisciplinary tapestry illustrates a deeper truth about the nature of scientific discovery. The universe does not care about our human-made categories of cosmology, particle physics, or materials science. It is a single, coherent system where the laws governing the unimaginably large are deeply connected to the laws governing the impossibly small, and both can be reflected in the complex behavior of materials right here on Earth. The search for the magnetic monopole, perhaps more than any other pursuit in modern physics, forces us to embrace this holistic view. It teaches us that to find answers to the biggest questions, we cannot afford to work in isolation. We must build bridges between disciplines, share tools and insights, and recognize that the spark of a solution might come from the most unexpected corner of the scientific universe. This collaborative, boundary-crossing spirit is not just a helpful strategy. It is the essential engine driving us toward a more complete and unified understanding of the cosmos, from the vast expanse of space to the intricate order within a crystal. The story of the magnetic monopole is not just a tale of equations and experiments, but a deeply human saga, driven by individuals whose curiosity and tenacity have kept this elusive ghost in the machine of physics alive for nearly a century. It begins, of course, with Paul Dirac, a man so famously reserved and precise with language that his colleagues at Cambridge University jokingly defined a unit of speech called the Dirac, 1 word per hour. Yet from this quiet, intensely focused mind emerged one of the most audacious ideas of 20th century physics. In 1931, Dirac was not setting out to unify the forces of the cosmos. He was obsessively focused on making the nascent theory of quantum mechanics mathematically consistent and beautiful. His paper introducing the monopole was a masterpiece of logical deduction, born from a desire for symmetry so profound that he was willing to postulate a particle no one had ever seen. The legend goes that when a colleague questioned the boldness of his proposal, Dirac simply replied, "A beautiful idea has a much greater chance of being correct than an ugly one." For him, the monopole was not a mere possibility. It was a necessary consequence of a universe that made mathematical sense. He never won a Nobel Prize for this specific work, yet the Dirac quantization condition remains one of the most elegant and enduring arguments in all of theoretical physics, a testament to a mind that believed the universe's deepest secrets were written in the language of mathematical beauty. Decades later, as grand unified theories revived the monopole with renewed urgency, the baton passed to a new generation of experimentalists, none more emblematic of the patient, painstaking hunt than Blaise Cabrera. A physicist at Stanford University, Cabrera dedicated a significant part of his career to designing an experiment of exquisite sensitivity. He constructed a small, 4-loop superconducting detector, a device so delicate it had to be shielded from the slightest vibration and electromagnetic disturbance, suspended in a labyrinth of cooling systems and magnetic shields deep underground. For months, the detector registered nothing but the quiet hum of the universe. Then, on February 14, 1982, the chart recorder pen leaped, tracing a single, perfect stair-step signal. It was a moment of pure, unadulterated euphoria. The data point aligned perfectly with the predicted signature of a magnetic monopole passing through his apparatus. He had seemingly captured the impossible. The physics world buzzed with excitement. The Valentine's Day monopole became an instant legend. But science demands replication, and that single, perfect event never repeated. Cabrera, with immense intellectual honesty, continued to operate ever more sensitive detectors for years, but the monopole never returned. He never presented the event as a definitive discovery, always treating it as an enigmatic outlier. His career embodies the quintessential scientific virtue of perseverance in the face of ambiguity, chasing a ghost with relentless rigor, even when it offered only a fleeting, tantalizing glimpse. While Cabrera worked in the quiet of his lab, another giant of 20th century science, John Archibald Wheeler, used the monopole to expand the very vocabulary of physics. It was Wheeler who, with his characteristic flair for evocative language, coined the term black hole. He had a similarly profound impact on the monopole story by popularizing and deeply exploring the topological principles that underpin it. Wheeler was a master of the thought experiment, a physicist who could visualize the fabric of space-time warping and twisting. He saw the monopole not just as a particle, but as a topological defect, a knot in the fields of reality. He would famously use the analogy of a hallway carpet. If you try to lay a carpet flat and it has a wrinkle, you can push the wrinkle around, but you cannot make it disappear without lifting the entire carpet. The wrinkle is topologically stable. In the same way, he argued, a monopole is a stable kink in the cosmic field that cannot be smoothed away. Wheeler's genius was in translating abstract mathematics into tangible, physical intuition, empowering a whole generation of theorists and experimentalists to think about the monopole not as a point, but as a structure, a permanent feature of the cosmic landscape. The human element of this quest is also found in the stories of collaboration and the passing of the torch to vast international teams. Consider the shift from the lone experimenter like Cabrera to the colossal collaboration of Mo Edel at CERN. This experiment is led by spokespersons like James Pinfold, a physicist who coordinates the work of dozens of scientists from institutions around the globe. Pinfold's role is less about a single eureka, a moment, and more about the meticulous, long-term management of a complex scientific enterprise, securing funding, ensuring different detector components work in harmony, and fostering a collaborative spirit among researchers from diverse cultures and scientific backgrounds. The hunt has become a communal effort, a far cry from Dirac's solitary calculations. In a modern collaboration, a young postdoctoral researcher might spend years analyzing millions of plastic sheets from the Mo Edel detectors, searching for a single microscopic track that could change everything. Their story is one of quiet dedication, of believing that their small contribution to a vast, decades-long project is worthwhile, even if the ultimate discovery does not come in their lifetime. This shift highlights how the nature of fundamental research has evolved, now relying on the collective effort of hundreds, all united by a shared fascination with a single hypothetical particle. These personal stories, from the theoretical brilliance of Dirac to the experimental dedication of Cabrera and the collaborative leadership of modern teams, reveal a deeper truth about the scientific endeavor. The search for the magnetic monopole is a powerful lesson in intellectual courage and resilience. It teaches us that progress is not always a straight line of triumphant discoveries. It is often a path marked by tantalizing false alarms, decades of null results, and theories that are beautiful yet stubbornly unconfirmed. The scientists who walk this path do so not for immediate glory, but for the profound satisfaction of participating in one of humanity's greatest adventures, the attempt to understand the fundamental rules of existence. Their perseverance in the face of an universe that guards its secrets closely is a testament to the human spirit's unyielding curiosity. They are driven by the belief that the cosmos is ultimately knowable, and that even a ghost, if pursued with enough rigor and passion, may one day choose to make itself seen. Ultimately, the confirmed discovery of a magnetic monopole would trigger the most significant paradigm shift in physics since the development of quantum mechanics and relativity, fundamentally reshaping our most cherished theories and launching a new era of technological and intellectual exploration. It would begin not with a quiet addition to the periodic table of particles, but with a profound and immediate rewriting of our foundational textbooks. Maxwell's equations, the very bedrock of classical electromagnetism, would be updated for the first time in over a century and a half. That elegant zero in the equation for magnetic charge would be replaced with a new, fundamental constant of nature, finally establishing a perfect symmetry between electricity and magnetism. This single act would complete a chapter of physics that has long felt unfinished, validating the intuition of Dirac and generations of theorists who believed the universe favored such beautiful symmetry. But this is just the opening scene of a much larger revolution. The discovery would serve as the first direct, irrefutable evidence for the existence of physics beyond the standard model, providing a crucial experimental anchor for the sprawling edifice of grand unified theories. While GUTs have been mathematically compelling, they have remained in the realm of elegant speculation, their energy scales impossibly far from our direct reach. Finding a monopole would change all of that. It would be a tangible relic, a smoking gun from the universe's first moments, confirming that the electromagnetic, weak, and strong nuclear forces were indeed once unified. Its specific properties, its exact mass, its magnetic charge, and the way it interacts with matter would act as a cosmic Rosetta Stone. By meticulously studying this one particle, physicists could discriminate between the dozens of competing GUT models. Is the universe's underlying symmetry SU5, SO10, or something more exotic? The monopole's behavior would tell us, guiding us toward the correct theory of everything with empirical data for the first time. This would inevitably force a dramatic re-evaluation of our most ambitious frameworks, including string theory and the quest to incorporate gravity. A confirmed GUT monopole would present a concrete target for string theorists to explain. Does their theory predict a particle with precisely these characteristics? The discovery would either provide a spectacular validation of string theory's core principles or force a major and painful revision, depending on whether the monopole's observed properties match the predictions derived from the geometry of hidden dimensions. More profoundly, the monopole's very nature as a topological defect provides a powerful bridge between the worlds of the very small and the very large. Its existence ties the quantum behavior of fields directly to the large-scale structure of the cosmos, offering a new avenue to tackle the greatest unsolved problem in theoretical physics, the unification of general relativity with quantum mechanics. By understanding how such a stable knot in spacetime behaves, we might finally glimpse how to quantize gravity itself, seeing how the fabric of the cosmos can host both smooth curvature and discrete, particle-like excitations. The technological horizon would expand in ways that are difficult to overstate, moving beyond incremental improvements and toward entirely new physical principles. We've already touched on the potential for magnetricity and topological quantum computing, but the implications run even deeper. Consider the field of materials science. The ability to manipulate individual magnetic charges could lead to the creation of metamaterials with magnetic properties that are currently unimaginable. We could engineer substances with magnetic permeability that changes on demand, leading to perfect magnetic shields or lenses that could focus magnetic fields with the same precision we focus light today. This could revolutionize medical imaging, making MRI machines vastly more powerful and accessible, or create entirely new forms of non-invasive surgery and neural interfacing. The very concept of a magnet would be transformed from a simple dipole to a component that can be engineered and integrated into circuits with the same flexibility as transistors, spawning a new field of magnetronics that runs in parallel to our current electronics. On an even grander scale, the confirmed understanding of grand unification that a monopole would provide could unlock the long-dreamed of technology of proton decay reactors. While the idea of using monopoles to catalyze this process is daunting, the deeper knowledge gained might show us alternative pathways to achieve the same result, to safely tap into the immense energy reservoir locked within the protons of ordinary hydrogen. This isn't merely a more efficient power source, it is the kind of energy technology that could make interstellar travel a realistic prospect. A spacecraft powered by proton decay would not be limited by chemical fuels or even the bulky reactants of fusion drives. It could, in theory, harvest its fuel from the hydrogen that permeates interstellar space. Humanity would transition from a species confined to its solar system to one capable of crossing the gulfs between the stars, all because we deciphered the message carried by a single, elusive particle from the dawn of time. Beyond the equations and the machines, the discovery would trigger a profound philosophical and existential shift in our cosmic self-perception. It would provide the most direct evidence yet that the universe we experience is indeed a cooled-down, broken symmetry remnant of a far more symmetric and unified state. The forces and particles that seem so distinct and fundamental to our everyday reality would be revealed as frozen fragments of a grander whole. This realization that our reality is not the primary one but a specific, low-energy outcome is as humbling as the Copernican revolution that displaced Earth from the center of the cosmos. It suggests that the laws of nature as we know them are not necessarily universal or eternal, but are contingent upon the specific history and cooling trajectory of our particular patch of the universe. We would have to confront the possibility that other regions of the cosmos, perhaps beyond our observable horizon, might have cooled differently, resulting in entirely different sets of physical laws and fundamental forces. The magnetic monopole, therefore, is more than just a particle. It is a key to understanding not just how our universe works, but why it is the way it is at all, offering a glimpse into the infinite possibilities that were present at the moment of creation and solidifying our quest to understand the cosmos as the ultimate human adventure. And so, after this incredible journey across the cosmos and into the heart of matter itself, where does this leave us in our understanding of the magnetic monopole? We have seen that it is far more than a simple missing magnet. It is a profound prediction born from our most ambitious theories of reality. Grand unified theories which seek to weave the electromagnetic, weak and strong forces into a single, elegant tapestry do not merely suggest that monopoles could exist, they demand it. These particles are not optional extras but are unavoidable relics, topological knots that formed in the fiery aftermath of the Big Bang when the universe underwent its first great phase transitions. They are frozen fingerprints from an era of perfect symmetry, carrying with them the secrets of why our cosmos looks the way it does. The very fact that we haven't found them in overwhelming numbers led us to the revolutionary concept of cosmic inflation, a period of hyper-expansion that stretched the infant universe, diluting the monopoles to the incredibly sparse density that allows our galaxy-filled cosmos to exist. This quest has taken us from the mathematical beauty of Dirac's equations to the intricate dance of emergent quasiparticles in spin ices, showing us that the concept of a solitary magnetic charge is not just a ghost, but a robust feature of physical law, whether manifested in a lab or awaiting discovery in the depths of space. The significance of this search stretches across every domain of physics and technology. For our fundamental understanding, discovering a monopole would be the ultimate validation of grand unified theories, providing the first direct evidence that the forces we see as separate were once one. It would complete Maxwell's equations, finally establishing a perfect symmetry between electricity and magnetism, and it would offer a tangible bridge to understanding the universe's first moments. Technologically, the potential is staggering. It could pave the way for magnetricity circuits that run on magnetic current, leading today to storage of unimaginable density and stability, and to quantum computers built on topologically protected qubits that are immune to the decoherence that plagues current design. It might even unlock energy sources that tap directly into the mass energy of protons, revolutionizing power generation and opening the door to interstellar travel. Yet, with such power comes profound responsibility, forcing us to confront the dual-use nature of a technology that could unravel the very fabric of matter, demanding a new era of global ethics and cooperation. The enduring mystery of the magnetic monopole serves as a powerful reminder that our exploration of the universe is far from complete. This is not a story of failure, but one of persistent, exhilarating inquiry. The fact that we have not yet found one, despite decades of searching with ever more ingenious experiments, is not a closed door but an open invitation. It challenges us to think more creatively, to build more sensitive detectors, and to refine our theories with even greater precision. This is how science truly progresses, not only through triumphant discoveries, but through the dedicated, collective effort to understand the unknown, even when it remains stubbornly out of reach. The hunt continues in deep underground labs at particle colliders and in the data from cosmic ray observatories, each null result sharpening our questions and guiding our path forward. This is where you come in. The story of the magnetic monopole is a testament to human curiosity, a quality that doesn't belong solely to physicists in lab coats. It is a spark that lives in all of us. I encourage you to carry this curiosity forward. Follow the ongoing research from places like the MOEDL experiment at CERN or the results from neutrino observatories. When you hear about a new discovery in cosmology or particle physics, ask yourself how it might connect to these grand, unanswered questions. Share this sense of wonder with others. Talk about the incredible idea that a particle from the beginning of time might be drifting through your room right now. The greatest unsolved mysteries of science are not just puzzles for experts, they are an open invitation for everyone to marvel at the complexity and beauty of our universe. Stay curious, keep asking questions, and remember that the next great discovery, the one that rewrites our textbooks and changes our world, could be just around the corner, waiting for a sharp mind or a sensitive instrument to finally bring it into the light.